everyone, and welcome to Let's Stump Jen. This week I have a really special guest. It's Matt, who is almost a doctor.
Hopefully
soonish. Matt, if anyone hasn't seen him on our Synosium streams or checked out his own stream, please go and sub to him. I think Matt's put his link in the chat, but I will add it to the description later. But in the link in his Twitter link is in the link that I sent out on Twitter, so please go and follow him and sub to him and all that stuff. Matt is a physicist who specializes in lasers. Well, is that right? Specializing in lasers? Optics is your field to a certain extent.
Yeah, my field at the moment is actually gas detection, but I use lasers.
You use lasers for it, yeah.
And last year when I was doing honours, my specialty was in a particular field of lasers called polariton lasing. And my first author publication, which is the first time I've been able to publish a paper as my paper, was actually on that, where we found a new material where you essentially have a matrix of some polymer, so like a plastic. It absorbs all this light and then feeds its energy to a second molecule, and it does this other really weird lasing thing. And while that's been seen in other ones, it hadn't been done yet in polariton lasing, and we managed to do it. So that was pretty cool. So,
wow.
Yeah. But now I use lasers to try and detect parts per million of methane, and we're trying to make really, really small detectors.
Your detectors might end up going on missions to Mars or Venus.
Never know. Our group does make CubeSats, though.
Yeah, and even CubeSats would be awesome.
This one has short range. It has to detect it there, but our group.
But
has
you could sacrifice a CubeSat. You could drop a CubeSat into an atmosphere.
Yeah,
and sacrifice it, get the signal back, and get a parts per million reading for methane in an atmosphere, and
which would be pretty useful, particularly when it's close by. And you could do it for other gases. You just need to have the right laser.
Oh yeah,
all about that light.
All about that light.
I was kind of thinking that after I said it.
Yeah, it's all right. I'm the one who made myself look stupid. I've got to be the one who's stupid this week because I got somebody who's getting close to their doctorate here. You're going to definitely be better at answering some of the questions than I am.
We'll see. Depends on the question.
It's going to depend on the question.
Don't ask me anything about sport. I can guarantee you that was stumped straight away.
See, this is what they do to me. They usually... because you've been in the chats before when I've done one of these, and they usually go down history or biology. And I go, yeah. I might be able to bullshit my way through some of those things, but not well.
I can do history.
You can do history. Oh, well, that's good.
So there's one for the chat. You can try me on history.
You can try Matt on history.
The areas that I like, I'm good with submarines as well. I do like my submarines, but I've done a couple of videos on them, so I don't know if that's cheating or not.
So, a paper came out was it this week that it came out? Because you've got it open in front of you.
Let me have a look at
it. It was fairly recent because the news article for it in Scientific American only came out this week. So I'm assuming the paper probably came out within the last month.
Yeah, published 3rd of August 2020, but it was first received on the 22nd of December last year. So it's been nearly a year.
Yeah.
But that's long. So probably they had a lot of questions about it, but that's not unheard of for papers.
Well, I'm not surprised given what it is and given the topic it's about and the importance of it to physics in general. But this paper has to do with quantum tunneling, which has, whilst we know it happens, the controversy about quantum tunneling has always been, is it instantaneous or does it take a period of time to happen in? So can it be a form of faster than light? Because if something tunnels through instantaneously, well, then you've got faster than light. And effectively, if it's a particle tunneling, you could communicate faster than the speed of light with quantum tunneling. Is this going to be a problem for relativity? Well, what this paper is about a group that in North America that have been doing some experiments to determine the speed of quantum tunneling. And the reason why I thought this would be a good paper to at least talk about is because A, they used lasers, and B, it's an awesome bit of physics. So the lead scientist on this, and I'm going to butcher this name, I just know I'm going to butcher this name, and I'm going to have it up in front of me or I'm not going to be able to say it, is Igor Litviniuk from Griffith University. Oh, he's actually in Australia, by the way. So the lead guy's actually an Australian, so I forgot about that.
He looks like the supervisor.
Yeah.
Yeah, so looking at, because sometimes they do the orders different.
So, yeah.
So it looks like he's the supervisor. He's the guy in charge of the group.
It was there were some of the other people involved with the study were from North America, and there was all sorts of studies done. That it was a very big collab sort of thing. I think there was about 3 or 4 scientists involved with the study. Yeah, so University of Toronto. So when I said North America, I was including Canada for all you Canadians who are now going to be upset with me. Which was Ephraim Steinberg, who's the co-author. They list a few other people who were involved with it. Paul Quate, Raymond Chao, were some other people whose previous work that they based off and stuff like that. But that I'm reading from the article, but Matt actually has the paper in front of him because
I do.
Being a uni student, he gets access to papers that I can't without going through a paywall. So we thought we might go through this study a little bit and try and explain to you guys what they actually did.
Yeah, so do you want to start off with what quantum tunneling is? Or I don't know where to start with. I haven't been on this show before.
All right. I could start off with that. As I'm sure a lot of you in the chat know, that particles, just like light, are both waves and particles. Everything is a wave and a particle, according to quantum physics. So when you have a particle that approaches a barrier, because it's a wave, there is a potential of that wave, and that wave can effectively move through a solid barrier that you wouldn't think a particle could. And because quantum mechanics comes down to a lot of probability about where things can be, there is a probability that the particle will appear on the other side of the barrier because of the continuation of the wave. But that's effectively how it is. Now that sounds like absolute garbage when you're hearing it for the first time, because you go, oh come on, that's just stupid probabilities and maths. The whole thing is, though, it is actually true because of this duality of particles in quantum mechanics. In nature, because they are, it's just not in quantum mechanics. We know there's this duality of particles where they're both waves and particles. Because this dual nature of things, this mathematical phenomenon that, the potential of where that particle can be can appear on the other side of the barrier, it does actually happen. Now, it doesn't happen all the time, but if you've got enough small particles approaching a barrier, it's going to happen. It's actually used all the time in electronics and things like that. Quantum computers are going to make a lot of use of it. And it's something we have to consider as we're making microprocessors smaller and smaller and smaller, because we're getting to the point now where some of the particles, the electrons and that within it, will quantum tunnel in between parts of the circuit because the circuits are so small. It is actually one of the issues that NVIDIA encountered when they released their new graphics cards, in that if the power supplies weren't good enough, you had an increased chance of particles quantum tunneling within the chip itself, and that was causing stability problems in their new graphics cards.
Yeah, because you think the particle is here, but the particle actually can be anywhere on this whole area either side of it as well, and then all of a sudden it shows up over here. But it's
because of the way the Schrödinger equation works, and because it comes down to probability. And oddly enough, our universe is very much based on probability and not actual definites.
As far as we can tell, but it also looks like there are experiments that have shown, we're definitely... nature has some intrinsic randomness to it, the best you can do is probability. But one of the other areas that's really good for quantum tunneling, or where we need it, and Jen brought me up because I failed to mention it when I was last talking about
I've actually
stars.
mentioned it already in one of these. But yes, go on, Matt.
If it wasn't for quantum tunneling, our sun would not be burning.
No.
Because it lowers the barrier, because the particles can jump barriers, which means you need an overall lower activation energy to get fusion, which has quite a high barrier to start. So the fact that quantum tunneling happens means we have a nice warm sun keeping us alive.
And the fact of quantum tunneling actually means that even large gas giants like Jupiter do actually produce a tiny, tiny, tiny amount of fusion, because you will still get a quantum tunneling at that size, but it's not enough to be considered sustainable fusion like you'd have in a star. And that's your borderline between, is something a star or a gas giant? Is the fusion sustainable? Is it continually happening? So it's quite fascinating. So if it wasn't for quantum tunneling, the barrier to the mass a star would need to actually perform fusion would be, I think it's about 4 to 5 times what our sun is before you can actually get fusion without.
That's about it.
Yeah.
But then you have a problem that you would actually have the burning run out earlier, and it would be able to fuse less atoms. So we wouldn't have any of the material that we're currently made of, pretty much.
No.
That was the case. But I think you mentioned we had covered this before. I think that with this paper, and the problem that they were doing was that if, say, the particle is here, but you've got your nice little probability wave either side of it, and then it shows up here, is that instant? Because if that's instant, you have a problem, because relativity says information cannot travel faster than the speed of light. So information cannot be instantaneous. You can't have something go from here to here with instantly. It just can't occur. So this paper with kind of a review that was kind of assessing everything and looking at the different experiments and then saying, all right, let's see if we can answer this question. How would you tell whether something being here and then suddenly appearing here is instant, or there's actually a time delay? So that's what they were looking at in this paper. And they say, we haven't had the final word, but they hope to have resolved some of the controversy. Yeah.
Do you want to describe the experiment that they did? Because I find that absolutely fascinating.
If you want, we can actually go through the abstract.
Let's go through the abstract. Yeah, I think that'd be interesting.
Right, let me just bring this abstract up in front of me. Sorry, I'd scroll to the conclusion, because any good scientist reads the abstract in the conclusion.
Yeah. So neither of Matt or I have actually read this. I've read the article that Scientific American did on this, but I hadn't grabbed the paper yet because it was behind the paywall. And then Matt and I were talking about this before we started, and I said, I really want to talk about this. And he goes, well, I might be able to get hold of the paper and we can actually discuss the paper. So neither of us have actually read the paper yet.
So our goal here is to see if we can not get stumped by this paper. Because my area of expertise is not quantum mechanics.
Neither mine.
It's not one of my greatest areas in senior physics, though I did pass, because I wouldn't actually be here if I didn't. So, all right. So this is Atlock and the Quest for Tunneling Time in Strong Field Physics. That was it, wasn't it?
Yep, that's one.
There we go. Abstract. The debate on tunneling times has always been full of contradictions, and the Atlock experiments that measure tunneling delays in strong field ionization are no exception. The current review presents the debate and discussions concerning the studies of tunneling times based on the Atlock technique. So we'll get into that in a bit. We review them with their implications and pitfalls identified due to lack of accurate strong field models that validate the observations and interpreting the measurements performed on noble gases. In order to provide a complete picture, the review begins with a background on some of the popular tunneling time definitions, most of them conceived during the late 1980s debate, which are often cited in the Atlock literature. We then discuss various Atlock experiments on noble gas atoms and their interpretations in context of tunneling time debate, the tunneling time debate. The recently performed Atlock experiment and numerical modeling using atomic hydrogen are also presented as an attempt at resolving the controversy. We conclude with the current status of the debate. So that is the abstract. And like most papers, abstracts are generally not written to be understood by people who are not experts in that field. You can be an expert in physics, but if you're not an expert in that field...
It's... Although this is fairly straightforward in that I mean, as this is a summary of other people's... and I've not my headphone out. As it's a summary of a group of different experiments that use this technique... they're basically just saying that they've reviewed the different techniques and the different times that people have calculated for quantum tunneling to come up with this result that they've got to. So it's... And of course they haven't actually explained what the technique is for measuring it, which is the bit I find fascinating.
I'm just trying to find where they do that. There's a lot of mathematical models here. Lots of maths, because I mean quantum mechanics at the end of the day is just really complicated linear algebra.
Yeah.
And that's the thing, because it's so unintuitive to us. The best you can generally do is make a mathematical model.
Well, I mean,
and it's in terms of trying to understand
people didn't understand it. I mean, the concept of quantum mechanics came from Einstein's paper on light, on photons and the duality of light, and Einstein himself did not like quantum mechanics.
No, he didn't.
He hated it. He thought it would be proved to be wrong. Yeah, I know he was part of the Copenhagen stuff, but he really wanted quantum mechanics to just disappear. Because it was not nice.
One of his quotes, which some people would, I'm sure you can guess who, have taken out of context, is God does not play dice. So he thought there was no randomness to the universe, because that was kind of what he considered God. So he was saying, no, it can't be. It's just our ability to measure it. But later experiments came along. So Bohr, well, no, not Bohr. Who's the other one?
Richard Feynman and Niels Bohr.
Yeah, I think it was Bohr, and then maybe Oppenheimer as well. They were like the opposite. They were like, no, it's all fully random, and it turns out the answer is partially in the middle. So you can have some predictability, but at best you're going to get when you get to the really, really tiny, it's just going to be probability.
Yeah.
And so, but this was an interesting...
Of course, Schrödinger as well.
I think it may have been Schrödinger. So there's been a few years since I've covered that.
Yeah, I mean, it was a few years ago. I mean, we're looking at nearly getting on towards 100 years of quantum mechanics.
When I studied it, that's what I was.
No, but I mean, it's been around that long, and some of these people were back at the beginning, like Niels Bohr and that. Yeah. So yeah, you're talking about the 1930s when these guys were discussing it, and that's 90 odd years ago. That's a long time.
Yeah. Although what I find a bit odd for this abstract, and maybe I could share screen to show it if you want. But they don't actually give their conclusion. Sorry?
I might not be able to do the shared screen. Sorry.
Okay. That's all right. We could just chat about its implications. But the odd thing I find for an abstract, they don't actually say what their conclusion is. It's
no, they don't do that.
Conclude with the current status
I was thinking that.
Like, normally you say what the end point is.
Yeah. Although, admittedly, the Scientific American article was very much the same, and they interviewed Igor, so I'm like, yeah, it wasn't until the end of the article that he really talks about what their result was. So it's like
there's a good point in the chat that I've just seen from Dog with a capital G. He said Einstein said the same about black holes, even though they were visible in his maths. Yes, I was actually looking at this. So I did a video recently on the Nobel Prize, and that was what it was about. So it was mental block for the name. Oh no, I should know this. I just did this.
I think this comes down to Einstein had a very similar idea about how that comes out in his equations to what we were talking about on Merostream, on Synesium, where we said that because we can't know what the things are like, what the physics is like in the center of a black hole, it's quite possible that even though mathematically you have a singularity, that the black holes themselves aren't actually singularities. Because the Planck distance comes into play once you get down to really small things, so there might be a limit to how much you can pack in a given area. In that sense.
There was another really interesting way of looking at it that came out of it. So this was what kind of some of the results in the maths of the first half of this year's. I thought Matt couldn't see the chat. Yes, I can see the chat. So, that came out of the maths that showed black holes were real was that. Sorry, I'm looking at the chat as well.
Yeah, me too.
Was that you can actually keep the maths going and show that you end up with like a mirror image universe where instead of having a black hole, you have a white hole on the other side.
Which we've never seen. So it's quite probable that there is this problem to do with our understanding of that, and something within quantum mechanics precludes a singularity. But we don't know. That's the crux of it. I mean, we can't see inside a black hole. All the black holes we know of are a bloody long way away, and we wouldn't want to get that close enough to try and have a look inside anyway. So we're probably
you could have a look
not
inside.
going to know.
The quest. Oh, sorry. You could have a look inside, and your question would be answered. It's just you're not going to be able to tell anyone else,
and you're not going to survive very long.
With a large enough black hole, you can survive apparently for up to a year in free fall before you reach the singularity and get crushed.
Yeah, but you'd be spaghettified before there, wouldn't you?
If it's big enough, the difference in gravity would not be enough. But yeah, as you got closer, you'd start to get
stretched to infinity. Well, I mean, given the time dilation caused by the black hole, you might fall for a year. But it's probably going to end up feel like a lot longer for you. You'll
see the universe going past really quick. So for you, it'll be faster. But if you watch someone falling into a black hole,
it takes forever.
You'll never see them actually fall into the black hole.
No. Because of the time dilation. Now, Jenny Morgan actually asked us a question earlier about why can some particles, e.g. neutrinos, pass through solid items such as our freaking planet and others cannot. That's because nothing is effectively solid.
Yes. And the easiest way to think about it is firing things at a net. Or a net of small dots. So I've got a bunch of targets. There's some distance for me. They're all very small, but depending on the size of my bullet will depend on the chance of it hitting something.
Yeah.
So if I've got a net that has a really big pore size, which is actually a good way to think of atoms, if you've got your typical atom, if you've got a nuclei that's about the size of a rice grain, the actual atom around it, the electrons, I think the gap around is about the size of 2 tennis courts. So that's from a grain of rice. So most of matter is empty space.
Yeah.
So if I'm firing my particle at it...
Yeah.
Oh, sorry?
I was going to say, what gives us the illusion of solid matter is the magnetic fields.
Yeah, and how light and electronic things interact with it. Yeah. Because the light will bounce off it because it interacts with the electrons. And actually, it gets into refractive index as well, that if you're looking through a window, you're not seeing the original light.
So when you get something like, if you've got a piece of wood and you smack it against your finger, the whole reason it stops is the electromagnetic fields within the particles themselves, not the actual particles. The particles never touch each other. Never ever touch each other. And when you're dealing with a neutrinos basically have no charge and are super, 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 super tiny. So when Matt's talking about that bullet that you're firing at a net, yeah, that bullet's like a grain of rice being fired at a large thingy net, and your chances of actually hitting anything are just so tiny it just doesn't happen, or very often.
So just reply. Someone did the trap said not true. Not even neutrinos can penetrate Trump's brain. You know what we should do then? We should use it as a neutrino trap and use it to try and monitor the universe. Maybe we can find some dark matter.
Trump trap. As opposed to a pen trap.
Yeah. So
are you suggesting that his brain is so dense that he's got a little tiny micro black hole in the center of his head?
Yeah, if it was any denser, we'd all be swallowed by his brain.
The only reason his orange toothpaste stays on is the extra gravity from the black hole in the center of his head.
Yeah, they tried getting the orange off, but it didn't work. Anyway,
it just doesn't work. Yeah.
Sorry. We're firing all these little bullets, and I actually have to explain a similar thing when I teach spectroscopy to year 12s. I need a way of explaining what the chance of the photon hitting or the molecules. The more molecules you have, the better the chance of doing it. The other thing too is also the size of your bullet. So if you have a really, really big bullet and you fire it at a net, you're more likely to hit something.
Yeah.
So if you think about the old Napoleonic era with you got cannons and muskets, and I'm doing that because because they were still using solid shot. You could use a big cannon and fire a ball at a group of soldiers, and the chance of hitting someone was quite great. It's a big ball; it's more likely to hit. But when you have something like a neutrino, it's like using a tiny, tiny little pellet, and so the chance of it actually hitting something is very, very small. In fact, we did the maths for a neutrino. This was something I did for my astronomy course in third year, and I still remember this calculation. Because there is a bit of a, I'm not sure what I'd call it, whether I'd call it a myth or not, but it's kind of a little nerdy science myth. If you wanted to have a 99% or 99.9% chance of detecting a neutrino, how much lead would you need? And it turns out the answer that goes with this myth is 1 light year's distance of lead. So we did the calculations to figure out if that's true, and it is. These neutrinos have what its technical term is the cross-sectional area, for probability, because that's how we're doing it. We're looking at the size of it, or the cross-section area of interaction. And yeah, it's just tiny for neutrinos. So they just bypass everything.
It's the thing that annoyed me most about 2012. Was it 2012? What was the one where their excuse for what happened?
The neutrinos are mutating. No.
Mutated neutrinos warmed up the Earth.
The whole point of neutrinos is they don't do anything.
It was so annoying.
I got one question in the chat that I might need to respond to. So someone say, if I look while we're on this I think this is to do with something I said earlier about the refractive index and then not seeing the original photons. If I look at a photon from Alpha Centauri, am I actually seeing a photon that has traveled here, or am I seeing a photon that was lit by a chain of other photons all the way from the start? And I quickly put in the chat both, but it's not that simple. It depends what's in the way. So. Yeah. And the thing is, space is not a perfect vacuum, but and this is actually how we can tell what the sun is made of, because the outside of the sun will absorb the photons coming off. So the sun is very, very hot, so it's got a very high, very large black body spectrum. So that's why the hotter the sun gets, the bluer it gets, the more energy. But our sun has this, it's nice, smooth kind of distribution of light that comes off just because it's so hot. But some of those photons will actually hit and be absorbed on their way out of the star. So there is actually a gas on the outside. Most of them will be absorbed, and then some of them won't be. But they'll still have to pass through that gas. So some of the photons coming out of the outside are not the original photons. What happens is they'll hit a lot of the atoms, They'll kind of be absorbed, interact with the electrons, but it'll all balance out and you'll get an identical photon coming out the other side. It's actually what happens with glass in the visible.
Yeah, the photon raises the orbit level. That's not the right term. What is the right term? Oh, geez, I hate it when I forget things. I've just stopped myself. They are orbital. Oh, the electron shell level.
Yeah.
So but the photon provides extra energy to the electron, which raises its shell level, but the want of the electrons is to move back down into the lowest form, and when they move back down, that's when they re-emit the photon, or a new photon.
Though you do have to be careful. If you hit one of the right absorption bands, it'll be absorbed, and the photon that comes back out will be a different wavelength. So it'll always be redder.
Which is why you get absorption bands, and you can tell what's in.
Yes. So that's how we know what the sun is, because we can look at what's been absorbed, and absorption bands are unique to each element. And not just each element, but each isotope as well. So hydrogen will have one. Helium plus will also have them. Will have unique ones each. So you can actually go through and you can do a balancing act with all these different formulas, and you can figure out exactly what temperature and what the sun is made of. It's one of the most accurate things you can do in astronomy. It's quite cool. I've done, it's a branch of spectroscopy. And I've done those calculations. You balance, it's called the Boltzmann distribution and the Saha equation. So one of them says, you put more energy in, that band should get brighter, it should get stronger. And the other one says, but eventually you're going to put so much energy into it, you'll just rip the electrons off. And then everything changes. So
I think as we've been sidetracked with questions, we will get through the rest of this. I am going to send out the invites to Sam and Jenny, who both actually wanted to hop in and talk with us. And but we'll keep the questions coming in. We'll keep going through the paper because it's interesting. So give me a second. And I'll shoot that out. Keep going, Matt. I was just letting them know I was going to do that.
Where does the photon go after it has excited my retina? Okay, this one, so when it hits your retina, it's actually absorbed. So it's absorbed by the rods and the cones. So it's no longer a photon. That energy is now electronic. It's absorbed by the molecules. And that electronic change allows for a chemical change, and then your retina can pass that to the brain as an electrical signal. Your brain, everything gets simplified a bit, but then your brain has to piece all the information together, and your brain takes a lot of shortcuts. That's why we got, not just blind spots, but we also have a refresh rate in our eyes that is not because of the chemicals, but actually because of our brain can't do it fast enough.
I love the fact that our biggest blind spot is actually caused by evolution itself, because we evolve with our nerve connections to our retina at the front of our eye instead of the back like octopuses are. So the nerve connection is actually in the way of us seeing.
Cuttlefish have better eyes.
Which is why our eyes move all the time, because it's our brain compensating for the fact that we've got this enormous blind spot right in the middle of our vision.
But and it's why birds always look really weird and they keep moving their heads around, because they can't move their eyes like we can, so they have to do the same with their heads. But I think one eye sees color a bit better than the other one, so that the other one gets a bit more shape. So it has to, bounce around. Oh, there's another one. Does absorption happen to light in a room full of mirrors? Yes. Metal will absorb, and you can there's actually what's known as a skin depth. So when you're firing photons at a metal, how far through the metal will the light get before it's faded? So the skin depth, the deeper the skin depth, or the larger the skin depth, the further the light will get. So even with a mirror, a very, very small percentage of the light will be absorbed by the metal behind it. So if you're in a room full of mirrors and you let a single photon go, and assuming the mirrors are shaped so it can just keep bouncing, there's nothing for it to hit, that photon will eventually disappear. Might be probability with a single photon, but it will eventually disappear. Which is also why lasers don't use metal mirrors.
Oh, yeah.
Even though they have mirrors in them.
Because, that'd heat them up for a start.
Yeah, so you end up using a different type of mirror that's known as a dielectric mirror.
Yeah.
All it does is try to avoid that problem.
You can use
do it
that. You can
phases.
also use we got Jenny here, except her device isn't connected, so I can't add you in chat. There she is. Let's add her in. People should be able to hear her, but they can't see her at the moment because I've got to turn her camera on.
Oh, that's okay. I'm just an avatar today.
You are, but I'm still going to turn your avatar on. No, wrong one. No, wrong one. The wrong one. Hang on. Let's turn a couple of these on, and there's Sam. So we got Sam, and I just got to figure out where I've got to put you, Jen, so that people can see you. Hi, Sam. How are you?
Oh,
Here we go.
it wouldn't be a live stream. Oh, sorry.
Yeah, it wouldn't be a live stream without issues. No.
Is that a full behind the bar selection I see on your dresser?
Yes, I was talking to Jen beforehand whether I should have removed it. I better not show what's in the bottom of the cupboard as well. I think it's a good thing that they're not empty.
I don't need to see your sex toys.
It's alright, we're not sponsored by them.
No.
But if they'd like
holding
us
them in front of me. Yeah. No, I've been growing that collection for a number of years. It's not, and it's actually growing, which means I'm not drinking them at as a fast rate that I'm obtaining them, which I guess is something.
I understand. I had a bottle of scotch once that lasted me 7 years. So.
Nice.
That's cool. So, should we get back to the paper? Well, was there some more questions that we missed?
Probably.
We were still talking about mirrors. Some of the mirrors used in lasers are actually internal reflections inside of glass or crystal, aren't they? So,
yeah. So one thing you can do with a dielectric mirror is that you actually rely on differences in refractive index to do it, because when you have a difference in refractive index, some light will be reflected. The easiest one to think of is glass. When you look at glass, it's shiny. You can see partially a reflection in it. And so, I guess mirrors generally have a metal coating behind it. It's about 3% of the intensity for just one layer of glass, or one piece of glass in air. But what you do is you have two materials, one really high refractive index, one really low. So at every single interface, you get light reflected, just because of the difference in refractive index, and you just layer them up.
yeah.
And you can get mirrors that are like 99% reflective, or by trying to reduce it, you can get a lower reflective, which is what you need for lasers. You need one mirror that's not fully reflective so the light can come out. Otherwise, what's the point? It's an internal laser. It's not going to do much.
Yeah.
And are you inferring kind of like a splitter where the glass is at a 45-degree angle?
No, you can also do that. Yes, you can have a splitter. No, I'm referring to just a plain mirror. Since I can't share screens, if anyone does want to quickly open my channel link in a separate window, the photo for my not my actual thumbnail, but the channel photo is a photo I took of one of those dielectric mirrors for the laser. So it's inside the little circle.
So yeah, the splitters are a similar idea, Jenny, that they just using the refractive indexes of the materials to cause it. Because like we said, if you use a metal coated mirror, it'd have to be front surface anyway. But if you use a metal coated mirror, the laser's just going to burn the metal off.
Yeah, you'll just pretty much burn your laser into nothingness.
Yeah.
So yeah, lasers tend not to use metals for mirrors.
Which is hilarious.
Diode lasers get a bit different. This one's really weird because it's also a purple,
you blinded me. Sorry.
Yeah.
Hang in, Sam.
This one's quite low. It's 1 milliwatt, so hopefully we don't do any eye damage.
Yeah.
Yes.
You should be wearing safety goggles.
Technical issues now.
At least we can hear you.
All right, that's good.
Bit soft, but that's okay. Oh, that's probably my headphones, actually. I've just realised that everything's a bit soft to me at the moment. I need new ones.
So fair.
I'm not finding your link.
Mine?
Matt.
Oh,
I didn't
maybe
put
I
it in the description yet. That's my fault entirely. Hang on, I'll grab it from Twitter and I'll put it in the chat whilst you guys keep talking.
All right. Now, yeah, so for those who've come late, my area of expertise is in optics. So I work in gas detection and I play with lasers, and I was working in particular type of lasers last year. Oh, there we go. Someone's...
Yeah.
Oh, Sammy did. Thank you, Sammy. Please go
Yes,
sub
Sammy
to
Direct.
Matt. Matt is brilliant. Yeah, I mean he's gonna his answers for questions are gonna be way better than mine.
Oh, you've got some pretty good answers. So,
Yeah,
so
not
you're
bad
setting
for
me
an
on a high
amateur.
bar here.
Yeah.
Although I do have a video coming out. My next video should come out tomorrow. I'm hoping I can get the editing done, and it's going to be on why Dr. Evil can't have his sharks with laser beams.
Lasers. And people should go and watch that because I've read the script and it is absolutely brilliant.
Yes. Yeah. So it's So if you ever want to know why it's not practical to attach a laser to a shark because it wasn't obvious enough, hopefully I'll answer that. I also have one on where the submarines fly. So if those are the sorts of things that you like, that's what you can find on my channel.
Do submarines fly?
Well, of course they do.
Technically, yes.
I mean, liquid's just thick gas, so...
But you run into a problem, but they're running at neutral buoyancy. Planes don't.
Though that's true.
Yeah.
Well,
Some of the principles are the same, though. That's why I said technically you could say a submarine is flying, but it's not really exactly the same.
I mean, if you consider a Zeppelin or a blimp to fly, then you can consider a submarine to fly. That's kind of the conclusion. But I do actually, as an extra in the video, have an example of a flying submarine.
Well, there was that TV show way back in the 60s about a voyage to the bottom of the sea. They had a flying sub.
Yeah. I think the Russians thought it was during World War II tried to come up with a flying submarine because they're quite desperate against the Germans. So one of their plans was you'd have a submarine that was also a plane, so it would fly over the enemy minefields, land under all the water, and then go near the enemy ships, torpedo them, and then get away. But it turned out to be too impractical.
That sounds stupidly impractical.
Yeah, that would be impractical.
Well, considering how much extra weight you have to have in a submarine so that you've got the strength in the outer hull to handle the pressures of the water.
Yeah.
Making it... Maybe if it was all nuclear powered, maybe?
1941 by the Russians? No.
Yeah,
way.
no.
Not with the tech then.
Yeah.
Hi, Godless Granny.
The Russians
Nerdy.
were using
Hi to everyone
tube-type
else in the
radios
chat
into
who we
the
haven't
90s.
mentioned yet. Sorry, Jenny.
I was just saying the Russians were using tube-type radios into the 90s.
Yeah.
Yeah. Although they did set off the Tsar bomber, which is the largest ever explosion anyone's set off.
Yeah. Yeah.
50 megatons. This
I
thing
don't know that they should really be proud of that, though.
They actually scaled it back because the scientists were too scared of what would happen if they'd set off a 100 megaton bomb.
Yeah, they were still concerned that you could set the atmosphere alight.
Yeah. I think it was just designed to show everyone. It's like, don't mess with us because we will destroy the world.
Yeah,
I wouldn't be surprised if that still happened, frankly. Although, honestly, Tangerine Palpatine is probably more of a concern for blowing up the planet at this point.
Not anymore. Well, not soon. Yeah, I suppose he could have a tantrum and do it, couldn't he?
I think you're more likely to save the world if you take a videotape of somebody getting pissed on by prostitutes.
I'm sure the videos for that already exist. Many of them. It is the internet.
Isn't that what Putin said he's got of Trump?
Is a photon from a flashlight, a torch, the same as a photon from a star?
at the same wavelength, they would look identical. So if I just had one of each, just a single photon, and let's trying to remember what exact wavelengths we'll get through, but let's just go with about 500 because it's it's a nice bluish one. If it was just a single photon, I wouldn't be able to tell where it came from. What tells me where it comes from is when you take a spectrum and so you look at lots of different wavelengths and you see what's missing and what isn't. That's what
because
tells
that
you
gives
where it's
you
come from.
your absorption lines.
Yeah. So I've set it up. I even have a video on my channel where you can set up a basic spectrometer, and you can tell what the element is. You just heat the element; it'll give off its particular wavelengths. You can split them up and look at what the colors of the bands are, and be like, "That's mercury. That's hydrogen. That's helium." And with a bit of extra maths, you can figure out what temperature it is.
If I'm looking at a laser beam, or somebody takes, say, a 532 nano laser and shoots me across the street, that beam, of course, diverges. What happens to the photons that have diverged?
So the individual photons still have to kind of travel in a straight line. So when you actually model divergence, you can use divergence angle of theta. So it's like that. Most light sources do this. They spread out. Those photons are still traveling in a straight line. Just if you've got a detector, the density of the photons hitting it is less.
Yeah.
This was my last video I had on my channel, was showing laser divergence, where we went outside and we did it bit further than across the street, and it becomes quite obvious. They just spread out. It's like a flashlight.
Yeah, I think saying they spread out
parallel.
is the misnomer there, really, because it's even the laser light still isn't completely coherent. It's not completely parallel.
Yeah. It's just very close to coherent.
It just a lot closer than what a normal flashlight would be.
And
we
that's
can't
why
get closer than that yet.
If I take two separate laser beams, or flashlights, but lasers be a better example, I guess, and I cross them and they intersect precisely at whatever angle you want to precisely set up, why don't they interfere with each other?
Well, it's actually very hard to do that in the first place, but that's how things like Michelson-Morley work. So if you've got a Michelson interferometer like they do at LIGO, that's what they're doing. And they're relying on the fact that when the light comes back and it is interacting with each other, you will get dark bands and you'll get light bands. And by looking at how those change, you can tell the change in the depths. Now, Michelson and Morley, that original experiment, was to show there was some ether that were flowing through, and if you spin the thing around, the light's traveling at different speeds. But now they use it to tell changes in space-time. That's what LIGO is. But I think LIGO's due for an upgrade. I think they're going to upgrade them, so it'll go offline soonish. But that's what they're doing. You can actually do it. The only thing, as Jen pointed out, lasers aren't perfectly coherent. They diverge. So actually getting those photons perfectly aligned with each other is not going to be very easy.
Well, I forgive lasers. I'm not particularly coherent either.
You're better than Trump.
Indeed.
That's not a very high bar, though.
Oh yeah, like Boris is.
Boris Johnson is like someone threw a thesaurus in a blender.
Yes, Boris fuck off Johnson is something.
Yeah. Something else.
I mean, granted, a lot of my American friends have recently said to me that they wish they had Boris instead of Trump, which is not a high bar, but still.
Okay. Never again has brought up the Higgs boson.
Oh boy.
The God particle. I think the God particle is a ridiculous name for the Higgs boson. I know. I don't know who coined it. It's just ridiculous. And yeah, they did discover it. People misunderstand what the Higgs boson is about. That they're like, so the Higgs boson is responsible for mass. A small amount of mass is what the Higgs boson is responsible for.
It's responsible for some mass.
Some mass. a very small amount of it when you're talking about a particle, because most of the mass of a particle comes from its energy, because energy equals mass.
Yeah. It's responsible for the mass that we could detect that we didn't know where it was coming
It was coming from. Yeah.
Yes.
And
it was like an accounting thing. It was kind of like, well, these balance sheets need to equal each other, but we've got a gap here. What's this little gap?
So what's causing that? So there should be another particle to fill in that gap, is where it came from. And then the hard part was figuring out where it should be and then finding it in a really, really powerful detector like the CERN Super Collider.
Yeah.
Which was a very hard part to do.
When you see, you know, as a layperson, I look at an image of the results, in air quotes, of that big ring thing.
CERN Super Collider?
And it's a bunch of
Large
lines
Hadron Collider. Yes, thank
out
you.
from radiating out or shooting out of the center point. What are those lines actually representing?
Oh, when they do the sets of the movement of particles, when they do the impacts of the two particles moving in the opposite directions in the collider.
Yeah, they never explain exactly what those things mean. They just say, "See, look."
They're looking for a flash on a screen.
Yeah, basically they're taking a photo of the energy trails of the particles as those particles decay.
And those lines are a very oversimplified version of the results they actually have. I've seen the room with all the monitors in that they use to watch the results, and it's significantly more complicated. I counted more than 200 monitors.
Yeah. I mean, basically it used to be all done on photographic plates. So, like, when Fermilab first started doing theirs, it was all photographic plates, but now they have detectors and it's all computer processed. So, they're more looking at the charts that are measuring the energy levels that come off in locations, but they can still give you an image of what the trails are. And basically, they're measuring how long they last for, gives them an idea of how much energy each of those quantum particles had.
Okay, so
by the different energy levels, you can tell what they are. Sorry?
So the further from center that line goes, the more power is associated.
Yeah, how long it lasts for as well. So there's a measure of energy, spin, and how long it lasts for. I couldn't tell you exactly how it is because quantum mechanics isn't my thing, but
when they give you like a series of lines, it's basically spot the odd one out. This is the interesting one to focus on.
Yeah. And then by how long it lasts for, how it spins, etc., which they can see from the plates or from the detectors, they can determine what its energy level is, and that gives you the mass of the particle.
Okay.
Because energy equals mass. equals mc squared.
Oh, it does not.
It does, though. It really does. There are it's one of. I mean, we talk about how well general relativity is proven, but I mean, of all the equations Einstein came up with, and I realize E equals mc squared is not part of general relativity. It's a doodle he wrote in his notepad. So he was writing maths instead of drawing actual doodles, which is what lots of other people do. It was the equation he came up to. You can derive it within general relativity, I believe, but I've never actually done it. But he actually doodled it in the side of his thing. But it is probably the most tested thing within Einstein's equations, that E equals mc squared. If we didn't have it, you couldn't have nuclear power. You couldn't have. We wouldn't have had nuclear weapons. No. There's a whole lot of things in physics that just does not work if E equals mc squared was wrong.
And it's part of why relativity works.
Yeah.
Yeah. Ooh. I've lost audio.
You've lost audio. We can still hear you.
Oh, no, it's back. It's back. All right, there you go. Sorry, I lost audio for a second. Yeah, my two favourite conclusions from that, from E equals mc squared, one, hot objects are heavier, so if I take a brick and I heat it up, it gets heavier.
Or
Really?
the
a
second
glass
one,
of water,
because
and
that's
then
what it means. I'm putting energy into it.
and then
so
you put it
now
in the
has more
microwave
energy,
and
so
you
more
warm it
mass.
up. That
More
glass
mass
of water
equivalents.
gets heavier, and you can measure this.
Yeah.
That's just crazy.
Yeah, and my second favorite one is because photons, even though they have no rest mass, they still contain energy, so they do have mass, and I guess they have momentum. You can actually make a black hole using light. If you can squish enough light close together, you end up with enough mass equivalence that you end up with an event horizon.
A mutual friend of ours, well, mostly a friend of yours, actually wrote, well, not a paper, but he was involved with writing a paper on that very thing, as in Dr. Carl.
Yes. He wants me to check some technology out for him.
You still haven't done that?
I've done it, but now he actually wants to get it. So he wants to get it's essentially a video mixer.
Yeah.
And his words were I'll get it. I'll give it to Matt. He can figure out how to use it and then teach me.
Oh, that'll be fun to play with, because it's not cheap what he's going to buy.
Yeah, it's like lots of fun toys.
Yeah, to him it was. He said, "Oh, it's not that much." I'm looking at you going, "It's $1,500." I wish that wasn't much.
Oh, so never again say, so if you heat water, it weighs more. If you freeze it, does it weigh less? As long as you didn't lose any of the particles in the process, yes, because you've removed energy from the system.
Yep. And go on, Jenny.
I was just going to ask you if that brick you heat up is actually measurable on a scale. Say
Not really on
scale?
our scales, like day-to-day ones. Like we wouldn't probably be able to get hold of this stuff to do it, because I mean,
but
Eagle's
it has been
MC
tested with water.
Yeah, so you can, if you have the proper equipment, yes, you can do it
And test it.
But if we're talking about scales we'd find around the house, no way.
No, they're not nowhere near.
Is not that big, but it is a change.
Yes,
Yeah.
it is there.
So the temperature that you'd have to raise it to, or the amount of energy you'd have to put into the system, rather, in order to get a noticeable change on regular scales, is just insane. That it would require much more weight than any scales could handle in the first place that we've got. It requires specialized tech.
Yeah. Sammy Jenkins is jealous of you, Matt, because you're friends with Dr. Carl.
I guess he knows who I am.
Yeah. But, I mean, he knows who I am and knows who Marrow is as well, because we've interviewed him twice.
True.
So.
And, well, I've been into his office a few times, because
you've done better than either of us. Yeah.
He's not, and he's in normally only one day a week, but...
And he's sent you text messages and phoned you.
Yeah. He got me to help him with some calculations recently for climate change.
I have phoned him.
Sorry?
I have actually phoned him.
Yeah, he prefers doing things
people to
in
phone him
person
than talk on
or
Twitter.
over calls.
Yeah.
So if you want to get in contact with him, just call him.
Yeah, not that we're going to give you his mobile number or anything, because it's private, but yeah.
I think I've got it somewhere, but I don't remember.
I've got it in my phone. I've only ever called him twice. And they were both about shows. There was a question after that. Could lasers technically create a black hole if focused enough? You put enough energy in a location, it's the same as having the mass there. So energy can create a black hole just the same as a mass does.
Yeah. However, I do want to put one caveat. You won't be able to do that I don't think you'll be able to do that on Earth. So the largest laser, it's mainly due to our atmosphere. The largest laser on Earth is at the National Ignition Facility. It's the one they use for nuclear fusion. In other words, light has some momentum, so it can give a push. So what they do is they get a giant laser and they fire it at a pellet. It's the simplified version. You push this pellet of hydrogen fuel enough, and you squish it together and you get fusion. This laser, if it was focused any more than it is, it would end up ionizing the atmosphere. The electric field from the photons that it's producing would be strong enough that it would rip the electrons off all of the atoms in our atmosphere. This thing has like a half an hour.
It's ridiculously powerful. Yeah.
So it
Now-
takes a long time to reset this laser.
If we had a photon black hole, as it were, would the Hawking radiation for that function the same?
It should
I
do.
don't see why not.
Yeah.
Because once you get that black hole, and this is one of the problems with black holes, is that we still can't, or physicists still can't account for the loss of information. Because quantum mechanics says, no, that information has to be there.
Information paradox.
Yeah.
Now, there
So
was a
if that
paper written
information is
about
there-
that too in the last couple of months.
Oh yeah, we I think haven't we had 2 or 3 conversations about the information paradox, Jen?
Yeah, no, but there was an actual paper written on it where they think they might have come up with a solution for it. And it's got to do with they've done a similar thing to what Hawking did to work out Hawking radiation, where they figured out that over a prolonged period of time, the effects within the black hole will eventually make the black hole break down and explode. So you will have everything escape from the black hole eventually with enough time.
You get all the information back.
You get
Well,
all the
other thing,
information
too,
back.
is that once you get a black hole, once you've got that event horizon, anything you drop into it, you can still see.
Yeah.
So this is what. So if I took Jen and threw her
Drop me in
into
a black hole. Yes.
yeah. As Jen fell in from my perspective, she would fade to red and then slowly disappear. But if I still had like a radio detector, I could go to redder and redder wavelengths, and I could still see that image of Jen falling in the black hole. I would never see her fall in. So some of that information is definitely still there.
which is what
At
they
least
call
from
the-
Jen's perspective, she'd just fall in.
Yeah. And that's got to do with the holographic principle as well.
By the Hawking radiation.
Yeah. That's got to do with the holographic principle as well, where everything should be a projection on the event horizon. But yeah, I mean, it's also supposition really, because we don't really understand the physics in the middle of a black hole.
Yeah.
And we're probably unlikely ever to. Well, certainly not in any of our lifetimes.
No, I think it will probably, for most of us, always ever be theoretical, because we just can't go and test it.
No, and you certainly can't test it on Earth.
No, we're not making a black hole here.
That would go wrong.
Yes, but if you had the right size black hole, you'd be able to use it to heat your room very efficiently. I've done those calculations. It would only need to be tiny, but yeah.
If the Hawking radiation didn't immediately murder you.
Yeah.
Well, that's the thing. You can figure out what the size would need to be and how much radiation would be coming off it. And yeah.
The larger the black hole, the better.
Yeah, to a point. But once, like, if you converted the mass of our sun to a black hole, it would still, like, the amount of radiation would still be very low. Its equivalent temperature is only a few Kelvin. It's not much above absolute zero.
Our sun turned to a black hole, though, would not be particularly large.
No. So that gives you an idea that once you get to the bigger black holes, like the supermassive compact objects, the center of most galaxies, ours is about 4 million times the size of our sun, and the other one that they took the photo of was ours was 6 million. That one I think was 4 billion times the size of our sun. Yeah, their temperature
and there are bigger ones than that.
To zero. It's very little radiation.
And yet, if you grabbed the supermassive black hole in the center of the galaxy and shoved it in our solar system, it would only reach out to just past Uranus in physical size.
Fair.
The event horizon would.
This is like... I should know the answer to this, but I cannot remember for the life of me. How is it kind of theorized that black holes with moment work? I should know this.
So with what?
With moment, black holes that were rotating stars. Effectively.
I think what happens is they'll lose energy to gravitational waves, because if they're not perfectly even, because like the event horizon can be even because it's coming out from the center of mass, but what's inside of it may not be. It's
complicated.
Now I'm confusing myself.
But now you brought that up.
We do lose some of that information through gravitational waves. So when they had the black holes colliding and they had the chirp from LIGO, when they had the neutron stars colliding and they had the chirp from that. The actual information from the orbit is lost when they collide, and it's lost through those gravitational waves. So you can actually detect that, and that's why you get higher frequencies, but it gets louder. So it's the whoop that you get at the end. And it was exactly what they predicted, it's exactly what they saw, which is
Which brings me to something else they
idea
discovered recently about Sagittarius A star, which is our supermassive black hole, is that they don't think it's actually spinning. They think our supermassive black hole is not a spinning black hole, which is probably one of the reasons why at the moment it's not an active galactic nuclei, because they think that that's required to become an active galactic nuclei. For anybody who doesn't know, is a black hole that's actively consuming a lot of matter so that it can create the radial jets from either side of it. So, but yeah, and ours doesn't do that at the moment, although it has in the past because we had the Fermi bubbles, so it's quite obvious that it did at some point. So one of the things that came from that study was like you said, that over time the gravitational waves from a spinning black hole may actually slow it down till you get to the point where it virtually stops spinning. And but collisions of black holes, because they would have to orbit each other as they come together and eventually collide, might actually be what starts them up spinning again, because you've got that moment
induced by collision.
Yeah, moment induced by orbit, basically. So you might be able to figure out how long ago a black hole, if it was still spinning, actually last orbited another black hole, a supermassive black hole, by how fast it's spinning now. Which would be an interesting calculation from it. But that was a little side bit of the whole discussion that they had on it, but it's kind of interesting.
Sometimes with the calculations in astronomy, from my astronomy course, if you got in the right order of magnitude, even if you're a factor of 5 off, that was still reasonably accurate for most people. And the reason why,
especially when you're talking about something that's a long way away and incredibly big.
Yeah. So.
Astro has like stupidly big margins of error, but relatively they're quite small.
Yeah.
Yes, because when you're dealing with something that's in the order of billions, being a factor of 2 off, really,
that's nothing.
That much.
How heavy is the black hole at the center of the galaxy? It's this, give or take a few billion kilograms.
but it's already how many hundreds of trillions of kilograms.
So. Yeah.
I forget what our sun is, but it's 4 billion times more than that.
I mean, we do the same thing. I mean, it's like when you're talking about how big some of the largest stars are, like even Betelgeuse, it's like it's a rough estimate. We don't know for sure. We didn't even know for sure exactly how far away it was until recently.
Well, what if... Okay, so let's say our sun turned into a black hole that would compress itself down and blah, blah, blah. I don't want to hear anything about, it's not big enough to do. Let's just say it happens. How big would that black hole be?
If you give me 5 minutes, I can figure it out exactly.
Oh, all right.
It's not particularly big.
It's not particularly big.
No,
it would be quite small.
I think it was about the size. I think when they were talking about it, about the size of Manhattan.
I can do that maths. So if we collapsed, all I need is if I go find the mass of it, then I can work backwards.
If you're going to Google that, you might as well Google how big would the sun be if it was a black hole.
The mass of the sun is. I used to have this memorized for physics purposes, but I think 1.99 times 10 to the 30, I think, ish.
I think 10 to the 30 sounds familiar. Yeah, you're right. 1.989 times 10 to 30.
Well remembered, Sam.
I had to memorize it for the Astro part of my A level. Now, mind you, I never ended up doing the exam, so I've let some of it slip. But
well done.
Okay, so
I'm proud of you.
Here we go. If anyone wants to follow along with the maths, escape velocity is the square root of 2gm on r. So all we need to do is get r as the subject, and then we know that the escape velocity has to be the speed of light. We know the mass, g is a constant. So if you give me a few moments to do this, it's a bit late, so hopefully I don't get this wrong. I will soon have the exact radius.
It's not
very big.
No,
because we got a few factors in here that are going to make this small. It's 1 over, the escape velocity squared, and now I realize
we
I don't
say
have
it's
a
not very
calculator.
big. I mean, it's big compared to us.
Yes.
Oh, you need a calculator to do it. Well,
I could do it roughly without it because I can do cancelling of the powers and get close to the right order of magnitude. But no, what I'm going to do is because I don't actually have a calculator on hand, I'm going to do
You can always
the equivalent
use Google's calculator.
Yeah, but I also have MATLAB on my computer, so I'm going to do an extreme overkill.
That's better. MATLAB
Oh,
is better.
no, it wants me to reactivate the license key. Damn it.
Oh, dear.
oh darn it! I wanted the answer to like eight digits.
8 digits.
Well, format long and we'll get there.
Well, whilst Matt's doing that, why don't we go back a little bit to the original discussion, which was about the quantum tunneling. So basically, they looked at the ways that they were doing these tests to figure out how long it takes for it would take for the particles to quantum tunnel, and they basically figured out that it would take 1 attosecond or 3 something like that. I'm trying to find it now because I lost track of where we were at. That it does have a time frame, but they were doing the test by firing the test basically involved a laser and magnetic fields to manipulate the atomic state transitions of items. So basically, they use a laser as the barrier that the particle's going to tunnel through, which blew my mind. I was like, how's laser a barrier? But what happens is when these baryonic particles tunnel through the laser beam, they end up having spin imparted on them. And if you can measure the way that the spin happens on the particle, and when we're talking about spin in particles, it's not the same as something doing a top or anything like that. It's different. Spin is just a quantum term for an alignment of a particle. But you could measure the way it came out, the way that the spin was imparted onto the particle, and by that you could determine how long it took the particle to tunnel through the laser, which is kind of brilliant.
It's still very early days for all of quantum just yet.
Yeah,
and as such, it's not like we're going to suddenly be using this in all of our tech, but it is pretty cool.
Yeah. So basically, it changes the atomic clock of the particle as the particle moves through, and you can then measure the atomic clock of the particle and get how long it takes. So with their experiments, they found out that the particles were spending 0.61 milliseconds within the barrier. So it's not instantaneous.
Yeah.
But the bit that blew my mind about the whole thing was the fact that they were using lasers as the barrier.
It's still got to pass through something that contains energy. So
yes, it does, but it was like, I would not have... in all my days, I would not have thought of using laser as a barrier. I mean, I know you can use lasers as tweezers to pick up particles, So because light has energy, so it can move things.
A laser is probably the closest thing we can have to an actually solid object in terms of space occupied.
Space occupied, by the particles in motion, the waves in motion, Well, everything is a wave and a particle. We are waves and particles. So why should a laser beam be any different to any other thing? And if you're only firing individual particles at this wall and seeing which ones tunnel through it and which ones don't, because you could also have the particles just totally miss the photons and just move through, but then they don't tunnel, so they don't get anything imparted on them.
And
so they don't become quantum entangled, and it doesn't change their quantum clocks. So, so you could tell which ones that came through over the other side were ones that had tunneled and ones that had just missed everything and gone through. And you could also tell, of course, the ones that bounced off the photons in the laser beam. So, it's kind of brilliant that they were actually able to measure how long it took particles to quantum tunnel.
In my computer science lessons, probably my favourite explanation of quantum tunneling occurred. And the explanation was, sometimes when electrons are moving through wires, they jump from one wire to another, and therefore we need check digits.
I like that.
Therefore you need what?
Check digits. When you are programming a byte of information, you will sometimes, for example, only use the first 7 bits of that 8-bit byte, and then the last bit will be a check. So if you tell it that there are an even amount of ones, so you'd put a 1 at the end, you can do it either way around, then it's going to look at it and go, okay, was there some interference here? And it doesn't work in every scenario, because if 2 bits were affected, that's going to cancel it out, but it works most of the time.
Kind of like a checksum in a communications packet.
Pretty much.
Okay, Nerdy Rodent asked the question, which would be faster, quantum teleportation? Well, I assume he means quantum teleportation because it's the only type of teleportation we can do, or quantum tunneling. Given that quantum tunneling we now know is not instantaneous, I would be going with quantum teleportation because that uses spooky action at a distance, which we think is instantaneous. But given that quantum tunneling itself has been shown not to be instantaneous, it's quite possible that spooky action at a distance isn't either. It's just incredibly fast.
But everything I've come across suggests that you can't really do anything instantly. You cannot send information instantly. That seems to be, when you're dealing with physics, tend to stick with the fundamentals. That will get you the furthest. You tend not to be able to break those laws, and that's how Einstein came up with relativity in the first place.
And one of the things to think about when you're talking about things moving faster than the speed of light, or how fast matter can move, etc., is that we're all quantum particles, and quantum particles effectively have a maximum speed limit, which is the speed of light. It's not about light itself, it's not about photons, it's about how fast these waves can move within the universe. And that gives an upward speed limit of anything that's made out of this.
Yeah. And if you have any mass, you cannot reach the speed of light. You get very close, but you can't.
You can't.
There's, momentum dilation gets in the way.
Yeah.
If my physics teacher heard me use the phrase speed of light, I'd get a funny look, because we always had to say speed of light in a vacuum.
Yes.
Because we had to learn how to explain things for exam boards.
Yes, I guess fair enough. But I mean, the refractive index of air is like 1.003, something like that, depending on what the temperature is.
I thought it might have been 1.0036, but it's around there.
Yeah, so it's quite a small amount, which means the actual speed change in our atmosphere is almost... Yeah. When dealing with astronomy, it's close enough we can call it negligible.
Yeah.
I remember doing a thermodynamics
that degree of
course.
magnitude again.
I remember doing a thermodynamics course in my second year of physics. It was my third year of uni. And the lecturer was talking about, because we're dealing with large numbers. When you were dealing with thermodynamics, we were trying to figure out all the arrangements that you can have for gas particles in a room.
Yeah.
And when dealing with probabilities, the amount of different ways you can rearrange it, it came to the fact that, what is 10 to the 23 between friends? 10 with 23 zeros, or 1 with 23 zeros, was such a small number in comparison to other numbers that we could ignore it and assume it was 0.
Yep. When you're approaching, well, not actually approaching infinity, but when you get that stupidly big.
Yeah.
Yeah.
Okay. So Dodgy asks, would beating the light barrier put the particle everywhere at the same time? Effectively, if you're a particle and you're moving at the speed of light, from the perspective of you, it takes basically no time to get anywhere.
Yeah, it feels instantaneous because time is interesting.
Yeah, because
Yes.
time is interesting. But from an outside observer, of course, it moves at the speed of light. And yet, for everybody, the speed of light is the same.
Yeah, it's
It's
like if I threw Jen
crazy.
in the black hole again.
The universe
She
was
would
made
see
by
the
a
universe-
very lazy programmer.
Yeah, it's very broken code. It
Very
works,
broken
but
code,
not
yeah.
very well.
Yeah.
Oh, by the way, I do have the calculation. I eventually got my
Okay,
MATLAB working.
cool.
So, if we collapsed the sun down to a black hole, then doing some rounding off, the radius is just under 3 kilometers.
Yeah.
Oh, okay.
So, to give you an idea, the Earth would have a radius of did I do diameter or radius? Let me check. I think it's about the Earth would be 2,000 times larger.
Yeah. Yeah, I believe that if for people who've been there, the example they use is the black hole will be about the same size as Manhattan.
Well, I mean, a neutron star would fit within Sydney. It's only about, even
Yeah.
the larger ones are only about 50 kilometers across.
Yeah.
And those were the sides that they saw with LIGO colliding. And that was still a big collision. They're just so dense. And a black hole is even denser. But there's this weird gap, while we're still on that topic, where you get neutron stars, and then obviously if they get any denser, you'll collapse them to a black hole. And you get the size of black holes. But there's this weird gap, size gap, mass gap in the middle, where we haven't detected anything. So neutron stars are all this size, and then as you increase the mass, there's a gap, and then all of a sudden you get all the black holes.
Yeah.
Yeah, it's like there is a something, we think, maybe.
Yeah. But we haven't found anything like that. Now, whether it's just because they do collapse to black holes, but they're too small for us to generally detect them easily, because there's meant to be a lot of them. That's how we actually managed to find them. This is what general relativity says. They're just going to occur. But
Tiny black holes could effectively be a large source of dark matter.
potentially.
Would there be a threshold for a black hole that anything under this threshold could not come to fruition of being a black hole?
Yeah, you need a certain amount of mass.
Yeah. Technically, I think there is a size limit, and then you also it might end up dealing with quantum mechanics. But the problem is, theoretically, you could do it with any size because you just need to compact it enough and you'll get an event horizon. But the smaller it is, the larger the Hawking radiation. So the tiny one will just evaporate too quickly.
Immediately. If you... I'm trying to remember. I didn't do the calculation personally, but I think Kurzgesagt basically ran the numbers in like if you got a black hole the size of... that had the mass of a 2-pence coin, the Hawking radiation would basically destroy the planet.
Yeah.
Oh, wow. Maybe we should try to make those then in the lab, eh?
So, Dog G just asked us...
It scales with surface area. So that's what I said. Like, if we collapsed our sun down to a black hole, it would be freezing. But if you had one that collapsed down to a 2-pence piece, so we're talking about the difference between 3 kilometers and a pence, a 2-pence piece, it would just, it would fry the Earth to nothing.
I like Nudi's question.
Chances are for our detection purposes, tiny black holes don't really exist because I don't think they'd be around long enough for us to ever detect them.
Nerdy's question was, how do we know how old a photon is?
A single photon? I don't think you can.
No, I would have thought that.
I do not know of any way that you'd know how old it was.
I can't think of one either. It's not like photons change over time. I mean, they can be absorbed and then you get a new photon emitted, as we've already discussed. But we still couldn't know exactly how long that, how old that photon is.
If you traced the trajectory of the photon back and looked what object would have been there at that time, I guess you could, in theory, work out.
But if you only had one,
individual photon, I don't see how you could possibly.
In practical terms, it'd be impossible, even if not theoretically.
Yeah, this is why it's really good to have multiple photons, because then you can do some basic triangulation. You can, because of the redshift, at least within the universe, figure out how far away an object is if you know what it originally looked like. So
Which is what's so good about...
Type 1a supernovae, I think it's Type 1a, supernovae as a standard candle. And that's how we figured out distances in the universe.
Spectroscopy also comes to our rescue here too, because spectral absorption lines shift as the light changes with the expansion of the universe. So we can to get an idea of how far away the light came from by how much those spectral absorption lines have shifted.
Well, if I'm looking at, I'll go back to Alpha Centauri, which is how many light years away?
3.7.
3.7 light years away?
No, not Alpha Centauri. Alpha Centauri is a bit further. 3.7 for Proxima.
Okay, well, let's take Proxima then. Whatever that distance is and however long that takes in light years, 3.7, isn't that photon that old?
No, because for the same reasons as we said before, because most of those photons on their trip through will have interacted with some of the gas that's in our not exactly a vacuum space and been absorbed and re-emitted. So effectively it's a different photon.
You're also dealing with something traveling at the speed of light, so relativity is going to mess with time.
Yeah.
So the photon is not going to run at our time.
Yeah.
So almost talking about how old things are in the universe becomes very complicated. Nothing happens instantaneously. By the time I even see you guys, even if I was looking at you in person, if you were in front of me, we would be operating at different times. Because of relativity, there would be a time delay between whatever you do and when I receive it. The speed of light, it just seems to be the universe's speed limit. And so what happens when you're traveling at that gets very complicated. But yeah, photons don't really have anything that changes. But if you get far enough away from sources, you won't be able to detect them. So if we had evolved in 1 trillion years from now, we would not have known there was a Big Bang. We would have been too far away from everything else.
Yeah.
We wouldn't see anything.
And it would be so redshifted that...
Yeah, you wouldn't
be able to detect
it. Too redshifted, too far away. We wouldn't know the Big Bang had happened.
Yeah.
So
the universe is slowly dissipating.
Yeah.
Yeah. What happens after that? Well, we don't know.
Well, it depends what caused the Big Bang, really. I mean, it depends on... See, this is the thing. Where all we know is that the universe, the section of the universe that we can see, our visible universe, started 13.8 billion years ago with a sudden expansion. That's what we can know. But those sudden expansions could be part of quantum probability, because we know we have virtual particles that come in and out of existence, and if you get a non-zero change in the average energy density in an area, you could have something like a universe come into existence, given enough effective time. Although there's no way to assume that there was any such thing as actual time before the universe started, but given enough effective time,
could there have been in theory, but
There could have been, in theory,
I think they think that you could have had either space or time. You could have one but not the other. I can't remember which way around it went, which is a bit
weird.
Yeah, I should know that.
It's hard to figure that sort of stuff out.
The universe is the whole universe, yes.
Yeah. But it is conceivable that what happens to us happens all the time. It's part of multiverse theory, but even within our own universe, that these expansions constantly happen. But of course, we're not as part of those expansions, so we can't see them. So the universe could constantly be evolving and creating new matter within it, essentially by quantum fluctuation, but we wouldn't see it. We couldn't see it because we're stuck within our own little expanding bit of universe.
Well, we're not actually seeing anything. We're just seeing the reflected light from it.
Yeah. So it's kind of fascinating. There's things that we can't know because of the physics of the universe itself. There's things we can't know. I mean, if we ever figure out how to bend space-time ourselves, you to build an engine that can do it, and we can travel. We can bend space-time, and we can create a warp drive, and we can travel effectively faster than the speed of light.
Star Trek!
Go Star Trek! Effectively, if you could do that, maybe we could travel far enough out that we could see an entirely different aspect of the universe. Maybe we could see what happens beyond our bubble, but maybe.
Yeah. And the other thing with that's really cool is that if you could bend space-time, you could beat the speed limit of light. So what you could do, you could take a giant telescope. You can travel really quickly out from the Earth. You turn around with that telescope and you could see everything that happened. You could see our past with it, which means you could theoretically go out, turn around, and see dinosaurs. You can see what it was like to have them on the Earth, but you would need a massive telescope. Because you'd be 65 million light years away by that point. It would have to be huge lens.
All right. Dog G asked about infinity. Does the Mandelbrot set prove infinity, or is it just a bunch of complex numbers? Well, yeah, the Mandelbrot set is just a visual representation of a equation in complex numbers. That's all it is. It doesn't necessarily it doesn't prove infinities, but I mean, we know infinities exist. I mean, between 0 and 1 there are an infinite number of real numbers.
So
or fractions.
That's fun because then you get into theoretical versus actual infinities.
Yeah.
And we've not observed any actual infinities except separations we can create ourselves as constructs. As far as I'm aware.
And you can have different sized infinities.
As well. So infinity as a concept definitely exists. It's not a number, though. You cannot think of infinity as a number. It's just a concept. Does infinity exist physically in our universe? No idea.
No. And the fun thing is that infinity is different to infinite.
Yeah.
Which the amount of times I've had to explain that to someone who wanted to present me with some theory as to, honestly, mostly how creationism's true, but and they try and use infinities to wiggle out of tough spots, and so I explained to them how subsets of infinities work, and that they can't do that.
Okay, so Nerdy asked us, if the universe is only 13.8 billion years old, how come the Methuselah star is older? It's not. It's just our way of measuring star has a margin of error, just like our measurement for the age of the universe has a margin of error. And the estimates for the age of the Methuselah star and our estimate for the age of the universe do overlap. It's just that the media likes reporting things that sound awesome.
Yes, forgetting how science actually works.
She works, yeah.
This goes back to astronomy not being very accurate.
Yeah.
You have big error margins. So if you're talking about something that's in the order of 10 billion years old with an error margin plus or minus 5, you could easily measure it as being 15 billion years old, even if it's not. It's just how it goes.
Nerdy said, if you bend space-time and look back at yourself, does that mean everything is deterministic? Now there's a big argument in physics, isn't it? Is the universe deterministic?
No, you couldn't still pass the information. I think you'd still run into information
You're just viewing something in the past, like we do when we look up into the universe. We can't change anything that happened in the universe, but we're looking back in time up to 13.8 billion years.
But then that gets into the question, I guess, of if you're passing through time, does time work the same going backwards? Which is a thing we've discussed before, Jen, and the answer is basically we don't know, but it can be useful to assume, yes, in theory.
Yeah.
Yeah.
Science likes to assume that the universe is
consistent.
Is consistent, and that time is symmetrical. So that we have a symmetric universe, so that if you ran time backwards, you get back to where you were. That may not be the
Quantum
case.
mechanics.
That may not be the case because of the randomness that we think exists within quantum mechanics. It may actually not be the case. If you could wind time backwards, you might not get back to where you actually were, which means the universe is random and not deterministic at all. From our perspective, you wouldn't know any different, though.
Nope. I find it really funny that, like, it's one of two things. Either the universe is deterministic, or the universe is completely random on a small scale and looks deterministic.
Yeah.
But I think sometimes people get really upset over the idea of it being one way or the other.
Yeah, I think you missed the point here that from our perspective, we travel along the timeline of the universe. You know, we're almost like little sections that are cut up, and we can't go back through them. We can look back at them, but we can't go back into them. We can only travel into the future. So even if that future is set, from our perspective, it certainly appears as though it's not deterministic and we have choices. Even if those choices were predefined, it does appear to us that we have choices and that it's not deterministic. If the universe isn't deterministic, then it actually makes very little difference, except for on some of the light. A non-deterministic universe would have some issues for general relativity, but they're only minor.
Yep.
And there's a couple of issues for quantum mechanics with a non-deterministic universe in the issues of symmetry. So we would not have a symmetric. You couldn't have full symmetry in a non-deterministic universe. That's not necessarily a problem because we haven't proved supersymmetry anyway. So
yep. I mean, it's interesting, but it's not necessary.
Yeah, it's interesting, but not necessary. Not having supersymmetry would probably rule out a universe that will possibly rule out having a multiverse. It wouldn't be necessary.
Which many world hypothesis you use?
Yeah, you don't use them. You don't need the many worlds hypothesis if the universe isn't symmetric. If there's not symmetry and the universe isn't deterministic.
Yeah.
Yeah, it's not required.
If we rule it out, it just means we don't have to have it.
No, we don't have to have it. Yes, that's what I meant to say. We don't have to have it at that point. So, did we actually answer those questions?
I have no idea.
There was one question in there I want to get to at some point because I got an interesting side note on, but it was to do with nuclear bombs.
Oh, go on, please.
No,
let's do it. We've done the quantum bit. Let's do the nuclear bomb.
I do have one fact that I want to bring up. This is actually one of the numbers I was helping Dr. Carl with. So, could we just create a nuclear winter to offset global warming? Yeah, but then we'd probably kill everything because it'd be too cold.
Yeah.
And we'd set a good portion of the Earth being radioactive. It's useless.
Yeah.
No, your best bet would be...
Go on, sorry.
Oh, so I was going to say, your best bet would be if you're going to do something like that, where you deliberately coat some of our atmosphere to reflect some of the sunlight or mess with it, you just better, spraying a certain amount of particles into the atmosphere that are shiny or reflective. Change the reflectivity of the Earth.
Or
either that, or we got to remove
the CO2. Build a huge array of solar panels and put them in orbit around the Earth in such a way, shove them in the Lagrange point that always sits between the Earth and the Sun, and reduce the amount of light that actually gets to the Earth. Of course, you'd have to
easier
build an
just
awful lot of them.
Stop messing with the atmosphere. But
I agree, but you could effectively put a barrier up to reduce the amount of light that reaches the Earth. It's actually a thing that was discussed about cooling down Venus, is that if you built enough solar panels at the Lagrange point and covered enough area, you could filter out all of the sunlight that gets to Venus and actually cool it down over time.
Yeah.
Doesn't help with the thickness of the atmosphere, though.
No. Have you not seen Jurassic Park? We're not supposed to ask if we should.
We just do it. Okay.
So, but there is one thing I want to say on that while we're talking about nuclear bombs, just the amount of energy that this planet is absorbing. So I do have a video on this if you want to have a look at my channel. So I go into the details. This is what I was helping our friendly Dr. Carl with. The amount of energy that the planet absorbs each day, extra energy. So this is the disequilibrium. Yeah. So the planet does actually absorb a lot more than this, but this is how much extra heat it's retaining compared to what it's losing, is equivalent to 400,000 Hiroshima bombs every day. That's how much extra heat is being pumped into the Earth.
Yeah.
Most of it in the upper 200 meters of the oceans.
Yeah. One of the things we could do is we could go and use a paint and paint deserts white, so they reflect more light.
You got to increase the reflectivity of the planet. Or you change the atmosphere. Those are your two main ones.
Yeah.
But yes, or you could do something. Yeah, stick some mirrors out there and try and stop the light getting to us.
Yeah.
Require that everybody's roof is white.
Or we can all just turn our air conditioners on and open the doors, right?
That would work too, sure.
And failing to understand how air conditioners work.
You got to pump energy in to make it
I mean, I guess if you created enough solar panels, you're actually and you absorb the energy and store it, then you're actually reducing how much heat is being retained. And because you're actually using solar panels for getting all the energy, we can rely less on fossil fuels, and so we get a double whammy out of it. So, no one likes that
way. No, that wouldn't work that way.
It does. If you're absorbing the energy from the sun, then you are reducing the amount of extra heat that's in the atmosphere.
That doesn't sound like it would be very effective. I mean, the net gain of that.
Well, I mean, it would be the double gain of it by having more solar panels, building a lot more solar panels, means that we would become less reliant on fossil fuels, which is brilliant for the environment.
Are we talking photovoltaics or
yeah, well, it doesn't matter how you do it. If you're using a heat exchanger to do it as well, you're pulling heat out of the...
Yeah, as long as we're trapping that energy and putting it somewhere.
It's putting it somewhere else, yeah, so it's not staying in our atmosphere. If we're storing it in batteries, of course, we're going to end up reusing it. But the double whammy is, of course, that we are then reducing the amount of fossil fuels we're using, which is helping the environment and ultimately going to help the planet in the long term.
Theoretically, we could take... your basic water-based solar panel and pump that water then into the ground to a certain distance and cool it down to 55, and then let it come back up to reheat again. And
then you're putting the extra temperature
that way.
Well, it's not a problem.
But we're still heating the planet up.
Yeah, I think we're just heating it up underneath.
Our best bet would be to stop the heat coming in. So either that's stop the heat staying here, so we end up reflecting more of the energy back out into space, or we block it. And the two easiest ways of doing that is, one, remove greenhouse gases from the atmosphere so it doesn't trap as much heat, or make the Earth more reflective. So that's kind of what happened a long time ago. About 500, 600 million years ago, we got a period that was known as the Snowball Earth. where you had a runaway reverse greenhouse effect. For some reason, a huge portion of greenhouse gases like CO2 were stripped from the atmosphere. They think it was because there was a lot of weathering and the new rock absorbed all this CO2, which meant the atmosphere started cooling down. So that the glaciers formed on the polar caps and started growing, but they're white and reflective. So the bigger they got, the more light it reflected, so the colder the planet got. And this just got runaway, and the glaciers, they reckon, reached the equator. And Snowball Earth, or Snow Globe Earth, where we just got essentially covered in ice. And it was thanks to some volcanoes that saved us in the end. So we nearly froze the planet over by doing the opposite. And and you get the opposite once that ice starts melting, it's less reflective, the planet heats back up.
Which
and
is
it was
the problem
after that
we've got.
event that you get the kind of explosion of life into the forms we recognize.
I mean, it's not necessarily... I mean, what we've done isn't necessarily long-term bad for the planet. We're not going... the mass extinction that we're going to create by warming up the planet isn't going to destroy all life on the planet. It'd be really hard for us to do that. It could kill us, and it could kill a lot of animals, but the Earth will bounce back, and we'll get new life forms evolving and everything like that. The Earth actually doesn't give two shits about us. We're the ones who have to give a shit about us.
Yeah, because...
Go ahead.
No, you go.
You go.
No. Trust me. Go ahead.
All I was going to say is, there is nothing in this universe that suggests that apart from humans, anything cares about us. This universe does not care about us.
The universe is entirely inhospitable.
I was just going to say, as long as whatever comes next doesn't think of incredible ideas like intelligent design, we should be okay.
I love the argument of, look how intelligently designed. The universe is designed for us. No, it's not.
No, it's not.
99.999% of the universe is fucking dreadful for us.
We created dogs. Sorry, just answering Microraptor in the chat. Dogs care about us. Yeah, but we created them to care about us.
Shall we answer Paul Kamish's question, which was a while back? So if the universe is 13.7 billion years old, how can it be 90 billion light years across?
Oh, I did know the answer to this.
Oh, really? I thought you would know the answer to this. Okay. Shall I start it?
See, if I see an edge 13 billion light years away, and I look the other way and I see the same thing, that means I'm somewhere in the middle, which means it's 26 billion at least.
But the light that we're seeing that's taken 13.8 billion light years to get to us is from a star that is now 45 billion light years away, and that's because of the expansion of the universe.
Yes, it's to do with the fact it's expanding in all directions, and the light that we see doesn't have to have traveled the entire expanse of the universe.
Yeah. So what we're saying is...
we probably won't be able to see the other end of the universe.
Yeah, the amount of time it's taken that light to get here, it has continued expanding.
Which is why we know the universe is 19 billion light years. Our visible, not the universe, our visible universe is 19 billion light years across, because we can calculate, based on the expansion rate of the universe, how far those objects have expanded away from us.
I'm only partly dumb.
No, you got it, Jan. It's fairly straightforward answer actually to it, but it's not. It's like most things in physics; they're not intuitive.
Yes, anything we evolved to understand our scale to survive on, like the savanna plains of Africa. We didn't evolve to understand black holes or quantum mechanics. It just is not meant to make sense to us. And I think Richard Feynman's quote, anyone who thinks they've understood quantum mechanics clearly has not understood quantum mechanics, I think sums up the entirety of today's conversation. We can do some maths and calculations, but it's not going to make sense.
I like Nerdy's little comment here. If you think the universe is designed for us, let me jettison you into space.
I'm now thinking of the Moonraker scene.
That's the whole silliness of the Goldilocks zone. You know, we weren't designed to, or excuse me, the Goldilocks zone was not designed to fit us. We designed ourselves to fit it.
Yep.
Yeah,
And you can live outside that. I mean, they're thinking there might be life on some of the moons around Jupiter and Saturn, like Europa, Titan, and Io, because they're not in the Goldilocks zone, and their energy comes from gravitational differences and tidal effects between them and the planet they're orbiting that keeps just enough liquid water, and if there's some chemicals around, that's
or
all
liquid
you need.
Anything.
Which just extends the Goldilocks zone out significantly further. And this is assuming the life would be anything like us, which it doesn't have to be, but you probably would need liquid water.
Yeah.
From my understanding,
I mean,
you probably wouldn't get away without it. There are some chemical solutions that might be able to do it, but I don't think they would be any more likely.
I mean, we talk about silicon-based life forms and things like that. The real issue is that even though you can technically have similar chain molecules with silicon that you get with carbon, they're not as stable, and they're a lot harder to make. And there's a lot more carbon in the universe than silicon.
Yes. The problem with silicon-based life is that if it came into contact with anything like our atmosphere, it would be destroyed fairly quickly.
Yeah.
Carbon being one level up on the periodic table holds on to its electrons a bit closer, which means when it forms bonds, it holds those bonds tighter. So it will let go of the other things. So it makes a good building block. You don't generally want a foundation that's likely to collapse as soon as anything messes with it.
I mean, it is possible. I mean, somewhere like Titan, which is a lot colder, so you've got hydrocarbons as liquid oceans and things like that. But I mean, you're still probably going to be dealing with a carbon-based life form, just using different chain molecules for the carbons.
What is it about silicon that says it would come in contact and destroy?
So silicon-based life, the silicon itself is not as stable a molecule as carbon is. The bonds, it's all to do with those bonds that you form. So we're all basically chemicals, but if you look at anything like DNA, proteins, our phospholipid membranes around all of our cells, pretty much anything, they're structured around carbon. So if you're thinking about building with Lego, carbon is like the solid block, and you put all the little attachments to it. And those attachments, when you switch the carbon out for silicon. Become weaker. So it does not take as much to break those bonds. So
the long chains you need to make things like DNA and RNA and all the various acids that work in and proteins that work in it as part of life for us, if you do the translation of that into the long chains of silicon, as Matt says, they don't last as long. They're a lot easier to be pulled apart by other atoms and stuff. So
that's not to say it's impossible. It's just the universe in its current state, with carbon being far more common. If you had both carbon and silicon in the same environment, you're more likely to get the carbon forming something that will last.
And I mean, it used to be a thing of like, in certain environments, we're probably going to find that silicon would be better at silicon-based life form would be better at surviving. But everything that we've seen from carbon-based life on our own planet shows that various different ways that carbon can combine can create things that can survive in almost anything. So there is no reason to think that in an environment where you might get a silicon life form evolve, a carbon one wouldn't evolve anyway. And if the carbon life form evolves because it's got a better chance of survival because of those bonds, it's going to end up becoming the dominant life form. So on our world, as our planet first cooled, it's conceivable that maybe both silicon life and carbon life started, but because there's more carbon, because the bonds are better, the carbon life won in the end.
I have a question. How come DNA is made up of the four chemicals that it's made up of, and not something else?
Oh, luck. From my understanding, there's no real reason that a lot of the chemistry that makes up our biology is the way it is. a lot of it was just circumstance. That's what happened to be there. So, but there are some bases. So most of the chemicals in our body, pretty much all the chemicals in our body, are arranged in a certain pattern. So it's known as chirality, where you can either be left-handed or right-handed. So if I put my hands up, they're not superimposable. I can't put my hands on top of each other. And chemicals end up the same way. And you can talk about them as rotating like right-handed or left-handed, as I said. Mm-hmm. And almost all the ones in our body are one and not the other, but because I'm not an expert in biology, I've forgotten which way around.
Isn't it right-handed chirality that's
yeah,
dominant?
You might be right.
Might be right. Sorry.
But they reckon that one might have come because of the sorts of clays and chemicals that formed in the early Earth. But yeah, I'm whilst I'm a chemist, I am also a physicist and not a biochemist. So
yeah, that's why I said we need Mero. If you get a chance to, everyone bombard Mero with that question on Twitter for tomorrow, because she actually knows it. So, but yeah,
I just want to tackle Microraptor's question while we're on it.
Let's do that.
The recent one, how likely is it that a second kind of carbon-based life evolved on Earth, but has either now disappeared or is very rare? I think it's quite likely, because when we talk about all life being related, we talk about the last universal common ancestor, or Luca. That didn't have to be the only one.
No.
Life may have started as a bunch of different cells, and the other ones all died off because they either weren't as good, they got in the wrong circumstance. Yeah, they got eaten, anything like that. And so Luca was the only one that survived. And so I think it is quite possible that there were, but not probably as, some like alien creatures living under the ground. But yeah, to talk about life does like living, and it will. It just doesn't really care what life.
Yeah, it just seems to be that our particular. I mean, technically, the path to life as we know it went down several different routes anyway, because it's most likely that all life on Earth started with just RNA and not DNA, and DNA happened later, because RNA is actually easier to form than DNA, and technically, you could say RNA-based life and DNA-based life are two different kinds of life. Just because one evolved into the other doesn't mean. Yeah, I mean the way the base works is slightly different. So.
Yeah, I mean, I would refer people to tardigrades, bacteria, and dinosaurs.
Yeah.
Those are three pretty different forms of life.
Yeah, yeah. So I mean,
tardigrades are infinite.
Tardigrades are infinite, and when they get big, you can use them to make a spore drive.
I think dinosaurs evolved.
That was horrid.
It was, wasn't it?
the science in that recent one, that was painful.
In Star Trek, yeah.
The recent one. Normally, I could deal with Star Trek because they didn't take their own science that seriously. So it was just like, yeah, okay, like they weren't trying to be scientific, but this one somehow made an effort to be scientific and screwed it up big time. I don't know. It annoyed me more than the other ones did.
It often annoys me when science fiction tries to be scientific and then really screws it. See, I can respect something like Doctor Who, which goes, it's wibbly wobbly, timey wimey, and doesn't bother with the science at all. But as soon as you want to start talking about the science and you screw it up, that really annoys me.
It's like you tried, but you didn't listen in science class.
Yes.
No, when you've got people trying to explain science in films, the amount of times that goes wrong because it's not cinematic.
Yes.
Yeah. There's lots of movies that do it, and it really, really bugs me. It's like, no! I mean, but we talked about one earlier with neutrinos.
Have any of you guys read the Artemis Fowl series?
I did.
I watched the movie.
Too long ago for me to really remember it. I read them when they came out when I was little or younger.
My favourite weapon that's ridiculous from there is weapons that create concentrated neutrino blasts to fry people.
No!
That would be a lot of neutrinos.
Yeah.
That would be like supernova level amount of neutrinos to fry anyone.
And they created neutrinos using a nuclear reactor miniaturized.
See, my
Neutrons.
It really annoys me when you have Star Trek phasers. Yeah, you turn the phaser up high enough, and you can vaporize someone.
You're not storing that much energy in a handheld device.
Yeah, and aside from that, if you had somebody standing that close to you and you put enough energy in them to vaporize them, you have just killed yourself as well.
Yes. Lasers, yeah. My first ever video on my channel was about how movies get lasers wrong, and one of the 3 main points was energy supply. None of these movies seem to have spent any time considering what kind of power supply you'd need to run a laser that could actually kill someone.
It's just... this is why we have projectile weapons, because they actually make sense.
Yeah, if you're in space, you wouldn't use lasers like they do in Star Trek. You just fire a solid object at the other guy.
Yeah, railguns. Railguns and missiles make way more sense than lasers as weapons.
Especially if you have like massive starships and you effectively create a large hadron collider, but with an exit route on the loop, you can fire things pretty bloody fast.
Yep.
Shields always blow my mind too in science fiction. It's like, oh, we've got this really powerful shield and we're going to block everything. Okay.
Where's the momentum
You have to put as much energy into the shield as the energy you want to stop. So if I launch a nuke at your shield now has to have the same amount of power in that little spot where I hit it with the nuke as my nuke does. You have just burnt a hole in your own hole.
Yes.
So it just doesn't work.
Momentum.
Momentum,
like
yes.
It's got it. The energy's got to push you somewhere.
It does.
Yes. Okay. PJ Smith is just saying Star Trek uses phasers, not laser. It doesn't matter. That amount of energy to vaporize a human is still blowing up whatever handheld.
Yes.
Lasers make no sense at all. Plasma weapons are a bit more sensible.
Yeah.
The thing is, the logistics of containing a plasma weapon in a handheld device.
Oh, yeah, no. You wouldn't have a handheld. But
No,
you
when
could
you've got
technically,
massive
if you had a
plasma
large
cannons.
spaceship, have big plasma cannons and fire big...
Oh yeah, plasma cannons are fair enough.
Plasma cannon would be... But
Yeah.
why would you when you can fire a nuke?
Actually, I think there's...
Go on, sorry.
I got to bring up the time that the Project Excalibur. That was when the US, for anyone who's not familiar with it, tried to develop a space-based defense laser powered by the detonation of a nuclear bomb.
Yeah.
Now, the reason they thought they needed a nuclear bomb was that lasers become less efficient as you get to bluer wavelengths. And they wanted to make it out of X-rays, which needs an obscene amount of energy. But you also can't make mirrors for X-ray lasers because you can't bounce the beam back and forward and let it build up. So they needed a very, very big power source to get this thing to run. And so somebody, I presume in a board meeting, half sarcastically suggested a nuke, and they rolled with it. And they tried to make an X-ray powered by the detonation of a nuclear bomb, but they had a problem that it wasn't quite as bright as they thought, and also they couldn't focus the beam, which if you're trying to target oncoming enemy missiles, not being able to focus your beam properly is a little bit of an issue. But it was just the whole part of the Strategic Defense Initiative with under Ronald Reagan, where the US tried to put all these weapons in space, and none of them turned out to be practical. Space is not a good place to have a fight.
Railguns were the best things that came out of STI.
Yeah, but your best bet is just have them on the ground and launch them up.
Yeah, launch from the Earth.
Because that's the other thing. If you fire a railgun in space, conservation of momentum, you've pushed yourself back too.
Yeah.
See, my three favourite ridiculous sci-fi weapons that I guess you could in theory use are giant fuck-off EMPs, efficient railguns, and plasma cannons that don't somehow negatively affect the ships they're on.
Yeah. See, that's the biggest problem with the plasma cannon. Once you've fired it, all that energy from the plasma is right next to your gun. You might be able to contain it inside the plasma cannon, but once you fire it, you've basically got a little tiny star next to your ship. Yeah. See, they don't necessarily make sense. The type of weapons we have now, nuclear missiles and railguns and that, are the sensible weapons that our current concepts of physics would come up with.
And in fairness, EMPs are a fairly reasonable thing to want in a space fight, because if you can shut off their systems...
Oh, they're fucked. Literally.
Yeah, just hope they don't shut yours or you don't shut your own off.
Off in the process, yeah. So,
which is actually probably a good argument for having a lot of analog systems on a space warship.
So
Also
do you want an
Faraday
answer to the
cages.
Fermi
On the
paradox
outside
as
we
to
have
why
big-
people haven't come and aliens haven't come and visited us? Because we're a violent species and they don't want to get hurt. Because
Humans are
even if
space
they've got
dogs.
better technologies to get here, we still have damn good weapons. And the laws of physics and the conservation of energy and momentum means that we could defend ourselves. Probably
Very
quite
well.
well against any aliens that
Yeah.
came here.
We
I mean,
are
it's
the
like the-
orcs of the real world.
Yeah. Yeah, we're the orcs of the universe. Big weapon.
But also probably why we couldn't go somewhere else, because if we try going somewhere else, it'd be the same thing. The advantage is almost always with the defender.
Oh, yeah.
Yeah, space warfare would go badly for whoever decided to initiate.
Yeah.
Yes.
Although, of course, the best weapon you could have is possibly your ship.
Smash.
Yeah.
No,
Or their
well,
ship, depending
not
how you
only
look
just
at
for moving fast. Just if you can create a warp field, if you could create a warp field around your ship and move at speeds that are faster than the speed of light, the what is it? The radiation that you create when a space moves, or the thing within space. No, when you bend this, when you can make something that appears to move faster than the speed of light. Chekhov radiation, is that right? I
That
can't-
sounds right.
Okay,
That
it's
sounds
blue anyway,
right.
like it is in Star Trek. If you're moving fast enough, that builds up in front of your ship as you're moving. So you just have to come out of your warp drive in front of the planet, and that big beam of fucking radiation keeps going and wipes everybody out on the planet.
Yeah. Alternatively, you build drone ships that do that and don't kill yourself.
Yeah. It's one of the things we'd have to figure out if we actually ever did figure out how to make warp drive, is that we'd have to
How
figure
to
out
not
some way of
murder everyone
dissipating
on
the
planet
energy.
below.
Yeah, or else you just kill the people of the planet's star system you're flying to. Maybe that's a solution to the Fermi paradox. There is a race out there that developed this, started moving around the galaxy and killed everyone. And then decided moving around the galaxy is not a good idea.
If we're going to do it, let's do this slowly.
Slowly, yeah. You even have the problem with relativity. As you get closer and closer to the speed of light, you build up radiation around the ship as it's moving, and when you slow back down at the other end, that radiation keeps traveling as well. So you have immense problems with moving large objects at relativistic speeds.
It's all well
Or
and
beyond.
good if you're going to somewhere you know is like desolate.
Yeah. I suppose if you aimed for the outside of the system, you could stop, but then you're basically shooting off something equivalent to a gamma ray in a particular direction, and who knows how long it will keep going for, and you might wipe out the next system instead.
I mean, chances are you're not going to hit. Oh, actually, no. I think with enough...
You got a good. If you could aim it right, you'd have a pretty good chance of not hitting something,
Especially if
probably.
Yeah. the
You
thing
aim
is
it
that
up.
If you did it many times, though, you would eventually hit something.
Accidents happen.
Yeah, accidents happen is the excuse we can give to whatever civilization we accidentally wipe out.
Oh, yeah.
Accidents happen. You
Okay.
just fried an entire planet of people.
Dog made an interesting point that if you explode nuclear weapons in space, you do actually create an EMP. Yes, you do.
Yes, but it depends kind of where you set them off.
Yeah.
They don't have as big a range as people expect. But actually, to get that effect on Earth, you only need to be about 40 kilometers up.
Yeah. but it still doesn't cover a huge area. And remember,
But the
space
US
is
did
big.
fry
It's
Hawaii.
amazingly big. You have no idea exactly how big space is. This is one of the problems with, like, if you were going to have space battles like you have in Star Trek, for one thing, it is really, really hard to see something tiny coming at you. So, even without shielding or ways of ships making themselves invisible or whatever else, if you've got a ship that's, say, the size of an aircraft carrier, a spaceship the size of an aircraft carrier, moving towards Earth, we would probably not notice it until it got, like, moon distance away from us, because that is kind of small.
Yep.
You know, that's smaller than most of the rocks that we're observing that are flying around out there. So, actually, and then, if you want to try and hit that before it gets here, aiming to hit that thing is going to be really, really hard until it gets really close. So, these really large battles that you see in science fiction, no, they're going to be over shorter distances because it's really, really hard.
It's likely also going to involve someone sending, like, mechanical arms to pierce your ship or whatever.
Yeah, you're more likely to launch solid objects.
Yeah.
And that's the other thing, though, is that in Star Trek, when they start, or any of them, you think, Star Wars, any of the space battles, they get really close and then they seem to move very, very slowly.
Yeah.
Yeah.
You have a spaceship.
Come to all stop. That takes a lot of energy.
yeah, but they also bank on a turn in a vacuum, so.
Yeah, I love that. I love how they're inside a ship with artificial gravity, and when they suddenly have to turn the ship fast, they all lean. It's like, what? No, that's not going to happen.
Just switch the artificial gravity. Although I think Star Trek generally at least says we've lost our... Was it the inertia dampers, or we've lost artificial gravity? So they try and come
I
up
love
with
that
excuses.
concept.
Yeah, they try and explain things, and it sometimes works-ish.
Heisenberg compensators. Because you can't actually teleport something.
Yeah, you come up with some bullshit MacGuffin, and you're fine in sci-fi.
Yeah. I mean, what we do when we were talking about quantum teleportation earlier, when you teleport a particle in quantum teleportation, you're not actually teleporting the particle. You are using quantum entanglement to read the spin and momentum of a particle and transfer it to another particle to make a copy of that particle. And in doing so, because of your act of reading what the original particle is like, you've actually stopped it being what it was originally. So you're not really teleporting, you're destroying and recreating, essentially. But it's not even the same particle, it's an entirely different particle.
Yep. It just looks the same.
It just looks the same. Now, could you scale that up to a macroscopic level? Probably not. You imagine quantum entangling all the particles in a human body. There's just no way.
Your body itself, it replaces itself, what they say, every 7 years.
Yeah.
Your body has replaced itself from cell regeneration.
Yeah, more or less. It depends on the part of the body.
Yeah, like blood will do it much faster, and there are some parts, I think, of... Is it bone or cartilage that doesn't actually replace?
I think I want to say bone marrow, but I'm not sure.
Yeah, there's some that's very, very slow, but yeah, generally speaking, it's every...
Biology is not my strong point either.
No. Give me lasers to play with any day of the week, which is why I have lasers on hand all the time.
Okay, Microrupt asks a good question. If you ignore the safety of it, would it be possible for us to travel outside of the universe? For that, we'd actually have to have a concept of what outside of the universe actually is.
We don't
know.
Yes. We don't know. But this is what I would say is really cool. If you could somehow move faster than light, or go between point A and B faster than light would get there, I think is probably the more accurate way of putting it. You could theoretically go out there, turn around, look back at Earth. I mean, you could look back at the whole universe, but
we don't even know if outside of the universe is a thing we can say.
Yes,
we don't know if that's a coherent concept.
And the other thing too is that they say that the universe is flat because what they the fabric of space time is flat.
Oh, we think so much alike, Matt, because this is where I was about to go.
Oh, lovely. So yeah, you can probably add more to it, but I'll try to give the basic one here.
Yeah, you do it.
What happens is that if the universe was curved, theoretically you could look out and see the back of your head if you could see far enough. Or
Depending on how it was curved.
Yeah, overall that fabric of space-time could be curved around in one way or another. But you can always measure a triangle and if the internal angles are 180, then you're in a flat plane. So that's what they did. Turns out the universe is flat. Problem with that is we're assuming we've got a large enough sample area
of the universe
to actually detect that.
Oh, the other thing, of course, is that it would be two-dimensional, but two-dimensional relative to what? Because we don't know if that's two-dimensional relative to another dimension we can't see, or a theoretical dimension, because imaginary math is fun.
Or if string theory is correct and there's like 13 dimensions to our universe.
Is it 13 or was it 11 and 2 time dimensions?
It's complicated.
Yeah.
It depends on the solution. Because some of them
Fair
go up
point.
to 27, so...
The day we could prove that would be amazing.
I would, wouldn't it? Well, we've already think that we've spotted cosmic strings, but cosmic strings don't rely on string theory being correct.
The two types of time are standard time and timeline savings time. you go back
Daylight
a millennia.
Those can replace A theory and B theory time now. We'll use that instead.
I'm being told off for questioning Star Trek science.
Yep.
And then there's metric time.
Metric.
Could we have tech downloaded to our... Could we have knowledge downloaded into our brains? Probably, eventually. Not in our lifetimes, I don't think so.
But eventually.
Well,
But
I don't
eventually.
see why not.
Yeah.
If we know how to manipulate the chemicals there, you could put memories in.
I don't know that we'd do that. I think there's more of a chance that we'll end up with little computers that are actually interfaced directly to our brain, and they'll be able to talk to each other through
Well, they're
digital
already doing
synapses.
that.
I mean, in fairness, they already do that to some level with amputations and where they attach prosthetic limbs that have sensory stuff.
Our brains are really good at learning to use things. So if you created an interface, your brain would eventually learn to use it as an adult. But if you actually implanted those into children, they'd learn to use it so much better than we could. So you'd end up, you could access... You got Wi-Fi in your head.
Alpha.
I mean, then you end up with something like Ghost in the Shell where people can be hacked.
Yep. And then you end up having to discuss with every ethics committee on the planet if it's a good idea to do that.
You could potentially solve a lot of problems, though, with it. Alzheimer's was one I heard years ago for that kind of thing. But, ethics committees...
with biology.
Okay. So Sammy's talking about if we had the tech to download minds, we could recreate the body and download the mind, in which case you'd kind of have a teleporter.
But it's the same thing. It's just destruction and recreation. Isn't it?
I see more of a call for us having like a remote controllable android bodies that can artificially make themselves look like us, that we can use the internet or a future version of the internet to remote into. So if you want to go and see a person who lives a long way away from you, you could go in your artificial body to see them. Or you could both meet up in an entirely artificial place because you've got these brain interfaces to the machine. So you could meet up in a virtual environment, which we're kind of getting to now with some aspects of augmented reality, but it's not quite the same as once you can actually plug directly into the brain.
I feel like you'll probably end up with, because of the whole ethics thing, something closer to Ready Player One.
Yes. Yeah.
I think we'll probably end up with something closer to that before we get actual brain interfaces, because we've got to wait for people's fundamental religiosity, amongst other things, to go away. Because the amount of times I hear the idea of playing God thrown around.
Yeah, I mean, I have issues in that we can't make secure systems now, fully secure systems now. So the act of
That relies
having,
on quantum shit to make things secure.
as we get better with quantum computers, yes, it's very probable that we can make fully secure systems, and then we could look at human brain interfaces and directly communicate and have good firewalling systems to protect our brains from attack and stuff like that. But up until then, probably some other form of really, really effective haptic feedback and really immersive.
Yeah. See, what will be interesting will be, I wonder how it'll be different, the way that you'd have to program someone's virtual mind for someone with versus without an inner monologue.
Yeah.
Do we really understand what the monologue is, though?
I mean,
Because we don't really know whether we all experience things the same.
I mean, I
We
was
can't
reading a
know.
thing that I think it said about 10% of people report having an inner monologue.
Oh, I guess I might be one of those.
Yeah.
But I'm
So-
reading that I sometimes have an inner monologue.
Explain
not
the inner
always.
monologue.
Being able to hear effectively hear your own voice in your head.
Yeah.
So when you're thinking thoughts, you think them in words.
Yes.
Yeah, I
I
do
would
that
think most people
fairly
do
often.
that.
I do that.
And I often think thoughts and then put them into words as well in my head.
Ah, yeah.
And the other one is that it completely baffles me. People who apparently only think in images. Because I've got a few of my friends who have said to me that they pretty much only think in images.
I can do both.
And I can do both, but I sometimes find I can't, and that I'm stuck just thinking in images or just thinking in words for a bit.
Yeah.
I normally have it like a video. It's a bit of both for me, where it's kind of like, yeah, mainly it is words, but I can do it where it's like I can see the scenario unfolding.
Yeah. See, my confusion with people not having an inner monologue is, but when people say that they've got a song stuck in their head, what do they mean if they can't hear that song in their head?
Yeah.
Well, this is the other thing too, is that like both we could all agree. Let me see if I get this right. That this is green.
Yeah.
Yeah.
And we can all point to that being green, but what I actually experience as green is not what you experience as green.
No, not necessarily, which is a fun thing, because how do we know how each other's brains is different?
More than likely it is. We've got hundreds of thousands of years of living together and creating these definitions over time. And the fact that we all have the same definition, I think, indicates that we're probably all seeing something quite similar to each other.
See,
Yes,
maybe.
but the thing you're missing from this, Jen,
out of that
is that
But language also has a lot to do with it because, for example, blue didn't exist until somebody came up with a way to make it in a paint color, and then they
as a
decided
word
they had
it
to,
didn't.
They had to, as a word, and they had decided they had to name it, and so it got the name blue as opposed to green. Green
it's a bit
was a
like-
name that was given to the sky.
It's a bit like, though, the fact that colours don't really exist. It's different wavelengths of photons that our brains interpret as colours. So
And
it's a
some of the
complete
colours our
psychological
brain
concept.
exists don't even exist as wavelengths of photons.
Well, that's back on what I
This
said
is
earlier.
true as well,
as a
because
semi-joke, that we don't see
Yeah.
anything. All we see is the reflected light from it.
Bloody
Yeah.
magenta.
Yep. Not a real colour.
I mean,
There is no wavelength of light that corresponds to it. But
Nope.
we see it.
Because otherwise it'd look green, and that'd be a problem evolutionarily.
Yeah, so our brain interprets it differently. And that's what it comes down to, what Sam and Matt were saying before, that when we see a colour, I might see green and you might see green, we might both say it's green, but does it actually look the same to both of us?
In
That's what we don't
photography, green and magenta are opposites, are complementary colors.
Well, yes, but if the brain didn't interpret it as magenta, that mix of photons would look green otherwise. And that's why the brain learned that as magenta.
I think technically our sun is green. The highest photon count from our sun, I think, falls in the green region.
Does it really?
That makes
think
sense
so.
because that makes a lot of sense actually, because the inside lights to me always look either fairly yellow or fairly
Blue.
See,
Red.
I was going to go red.
Red?
Blue
Okay.
blue is weird. Blue lights are always weird to me because I feel like I see blue lights less than other people see blue lights, but I see like written down blues stronger than other people sometimes. And I don't understand why.
On the Kelvin scale, daylight is around 6,400, 6,500 degrees Kelvin. And your basic indoor incandescent light is around 4,500, 4,800, something like that. Yeah, 3,000 gets bandied around too.
Yeah, 3,000. I've got some lamps in my room that can do 3,000. That's more when you think of the old incandescent bulbs. But when you got something, that would be warmer, like what I've got under my face now. I'm not going to shine it in the camera; it's quite bright. But the LEDs, the cooler ones, they'd be a bit hotter. It's weird because they call them cooler colors, but they're actually
hotter.
If you simulate thinking of black body, they're actually
well,
warmer.
that's why they call them cooler colors, because the Kelvin temperature is lower, and that's an old hangover from photography, the science of photography.
Yeah, and calories is a fun thing to explain to people. The fact that calories is basically a measurement of explosions.
Go on, I'm sure the chat wants to know, Sam.
Pardon?
Go on. I'm sure the chat wants to know.
Calories is a measurement of how much energy is in something, but to work out how much energy is in something, you explode it in a lab. And the body processing it and changing the energy into usable energy for the body equates to about the same as when you explode something. So the way they work out the calorie intake of food, so you've got a packet of chocolates or whatever, and they've got a calorie number on. That means that some of those chocolates have then been exploded to work out how many calories are in them.
You can also simulate the explosion by doing it as an electrical thing, so you actually turn it into a battery.
It doesn't have to be explosions anymore, but they still can.
Yeah, but your explosion
theory
exploding
food is fun.
The explosion theory also helps to explain flatus. Flatulence? I'm sorry.
Oh, flatulence. I thought you said something entirely different than Jen. Fellatio. That's what I thought you said.
No, that wouldn't explain that. Although there is an explosion at the end of it.
And it uses energy.
Hopefully. If you're doing it right.
Oh, no.
Alright, we've been going for 2.5 hours now. And I think Matt probably wants to get some sleep soon.
It's 2 a.m.
It's 2 a.m. for Matt, so...
Oh, you're in Australia?
Yeah, and he's East Coast,
I thought
he's...
you were in England.
No.
I'm sorry?
No, I'm the one in England.
Yeah, Sam's in England. Matt's in Australia. The other side of the country to me, though. So, whilst it's 11 p.m. here, it's 2 a.m. for Matt, so...
I'm 3 hours ahead.
Yeah, he's 3 hours ahead at the moment, so... I think we might wind it up there. This has been an awesome discussion. I have thoroughly enjoyed this, and I'm so glad you're able to join me for one of these, Matt, because it's been brilliant having you here. I hope we've been able to answer everyone's questions, or most of the questions that people asked.
Matt's a cutie. Matt, how old are you?
25.
Oh, God.
He's a baby. But he is adorable.
Oh, man.
So you are the youngest person in the generation above me, then? You're like the youngest millennials, effectively?
Yes.
Yeah.
And Sam, what's your age? I might as well ask.
Pardon?
I might as well ask what your age is.
18.
Yeah, Sam's young.
You're just too smart for your age.
Yeah, we're ancient in comparison, Jenny.
Yeah, well, I am. I don't know about you.
Depends on the day. But yes, I want to thank you, Jenny, and thank you, Sam, for joining us. It's always fun, and your knowledge is brilliant as well. So it's nice to have a team that can answer the questions, and I'm just not on my own. But I do enjoy doing these on my own as well, and I will do some more on my own. But it's nice to have guests as well, so that people can. Hopefully, we can actually answer the questions that get thrown in, even if I do get stumped myself. And thank you to everyone in the chat who's been following along. You're all amazing, and thanks for sticking it out as long as you all have. And please, everyone go and sub to Matt, Almost a Doctor, and to Sam. And what have you got? You already said what you've got coming up, Matt, because you've got Sharks and Lasers, which is going to be awesome. Please, everyone, go and watch that. It's absolutely brilliant. Like I said, I had a preview. So that's going to be brilliant. And Sam, what have you got coming up?
So, because I've just had a really low energy, bad mental health week, I didn't release last week's video. So I'm going to release that today.
Oh, brilliant. So everyone go and follow Sam and... Everyone go and follow Sam and follow on. And Jen, what have you got coming up?
Nothing.
Well, aside from Movie Night, are you guesting anywhere else? I mean, you're often on Dave's show.
Rumor has it I'll be on Critical Cripple's next show. He's changing the hours to the lockdown hours as he had before.
Oh, so I might actually be able to be on again. That'd be nice.
Maybe.
Yeah. Oh, cool. So he can have the two of us being disruptive.
Mm-hmm.
That'd be fun. We will have to drag Matt and Sam on.
I think they'd have a wonderful
to critical
time.
Questions. You've been on, haven't you, Sam?
I've sat in the chat and answered some of the questions once or twice.
Yeah.
And some of my answers are ridiculous and stupid to wind everyone else up.
Yeah.
Well, it's a great show, and everybody would have a wonderful time.
Yeah, it is fun. Dave asks questions that nobody really wants the answers to, and we answer them in as comical way as possible. Which is always fun. All right. So and thank you, Sammy Jenkins in the chat, who's been tweeting out everyone's links. So yes, please go and follow. Go sub to Sam and go sub to Matt, and and follow Jenny on Twitter because she's awesome and she's always appearing on other people's shows and she's always tweeting out when she's going to be on. So follow everyone. As for me, I may do another one of these midweek, but it will probably be not evening my time, but morning my time. I don't know if Matt wants to join me for that, if I do that, depending on how busy he is, and I'll give him a heads up. I'm hoping I can get either Scientist Mel or Mero to join as well, so that we can maybe answer a few biology questions a bit more accurately.
That sounds fun.
It does sound fun. So yeah, be looking at that, and hopefully I'll have some time this week to do a pre-recorded video as well, but I'm not guaranteeing on that because I've been so busy with everything else, and it also depends on what's happening with the new house. So more to come on the information with that later. So thank you again, everybody, and we will catch you all again soon. Bye.
Bye-bye.